Good morning, and thank you for joining us for the first day of the third annual SECARB GoMCarb Offshore Joint Partnership Meeting. I'm Ken Nemeth, the Executive Director and Secretary of the Southern States Energy Board. Before we begin this morning, I'd like to acknowledge the financial support provided by the United States Department of Energy and the National Energy Technology Laboratory toward this effort. We're proud to announce that over 120 participants have registered for this event, and as of right now, and we look forward to your questions and participation during the meeting. This meeting will take place over a 2-day period. The SECARB Offshore team will present our work today, while the GoMCarb team, led by the Bureau of Economic Geology at the University of Texas at Austin, will present tomorrow. Despite an unusually difficult year, our SECARB team has continued to make tremendous progress toward achieving the project's goals. For example, the team continues to characterize the geology of the study area and identify potential risks associated with the geologic storage of CO2 in shallow and deep water environments. Computational modeling efforts are identifying the reservoir properties that most influence plume dynamics in saline reservoirs and depleted oil and gas reservoir development strategies. Infrastructure reuse options are being evaluated, and novel, modular, subsea processing systems are being designed for the study area. Last, lessons learned from international offshore CCUS projects are being used to establish legal and regulatory best practices for the U.S. Gulf of Mexico. These activities represent only a portion of the SECARB Offshore program. More detail will be provided throughout the course of today's meeting. Importantly, these activities support the project's goal of improving the confidence in containment of CO2 in the offshore environment, while assessing the potential to implement commercial CCUS in the study area. Moving forward, the team will continue to characterize the geology of the Louisiana Shelf and Upper Continental Slope. In addition, budget period one modeling efforts and infrastructure assessments will be expanded. Finally, where appropriate, the team will engage with specific entities to discuss and develop regulatory processes to assist the commercial development of enhanced oil recovery and geologic storage projects in the study area. At this time, I'm pleased to introduce Dr. Ben Wernette, geologist at the Southern States Energy Board. Ben will briefly describe the SECARB Offshore project scope, introduce the project team, and provide an overview of recently achieved project milestones. Take it away, Ben.
Great, thanks, Ken. Good morning, everyone. My name is Ben Wernette, and I'm a geologist at the Southern States Energy Board. Along with Patti Berry, I will moderate today's presentations and Q&A sessions. The following slides provide an overview of the SECARB Offshore program, introduce the project team, and briefly review recent accomplishments. For those in attendance, we ask that you submit all questions using the Q&A icon at the bottom of your screen. Questions will be addressed once the session has concluded. If you would like to ask a question verbally, please use the raise hand icon located at the bottom of the screen. If time permits, you will be unmuted by the host to ask your questions. Finally, we ask that all questions related to Zoom connectivity be directed to Turney Foshi. We've provided Turney's email and phone number here on this slide for your convenience. Briefly, the SECARB Offshore team is tasked with expanding the membership of the Southern States Energy Board's existing Gulf of Mexico government-industry partnership to focus on assembling the knowledge base required for secure, long-term, large-scale subsea storage of CO2. The partnership's evaluation focuses on active and depleted oil and gas fields, as well as deep saline storage resources in the eastern portion of the Gulf's federal and state waters. On the right-hand portion of your screen, you will see a map delineating the SECARB region in the eastern Gulf and the GoMCarb region in the western Gulf. It's important to note that the Hanna district, denoted here, is shared between the two partnerships. As Ken noted during his remarks, this project is funded by the U.S. Department of Energy and managed by the National Energy and Technology Laboratory. The Southern States Energy Board is the award recipient and oversees the activities of the project team. The team is comprised of individuals with expertise in a variety of subjects. For example, characterization efforts are led by Advanced Resources International, Louisiana State University, Oklahoma State University, and the Geological Survey of Alabama. Commercialization scenarios are being evaluated by Aker Solutions and Pale Blue Dot. Risk assessment efforts are led by Crescent Resource Innovation, Battelle, Oklahoma State University, and Virginia Tech. Software and data management support is provided by SAS and Schlumberger. And finally, IOM Law serves as the legal and regulatory lead for this project. Over the last year, the project team has participated in DOE NETL meetings as well as internal project meetings. The team has also completed several project deliverables and milestones. Here, I've illustrated recently completed deliverables and milestones, as well as those planned for completion in the coming weeks and months. Importantly, the Task 3 milestone was submitted in January of this year, and Budget Period 2 is set to begin on July 1 of this year. At this time, I will turn things over to Patti Berry. Patti is Senior Geologist at the Southern States Energy Board, and she will introduce this morning's speakers and moderate the Q&A session. Patti?
Thanks, Ben. Our first topic this morning is assessment of leading practices and legal and regulatory frameworks. Our first speaker is Brian Hill from Crescent Resource Innovation, and he's going to talk about available and leading practices in the offshore. Brian is a finance and commercialization consultant who currently assists SSEB in a number of projects focused on accelerating CCUS development in the southeastern region. And after that, we'll hear from Ingvild Ombudstvedt, lessons learned from 25 years of offshore CCS operations, legal and regulatory analysis. She's a Norwegian lawyer and economist in the, I'm having trouble with my braces and it's hard to talk. And the owner of the law firm IOM Law, which was founded in Oslo in February 2017. She works on issues related to petroleum law and CCUS, both in Norway and internationally. And we'll take questions after both of our speakers. So, Ryan?
Good morning, everyone. I'm looking forward to the discussion today, and wanted to spend a little bit of time speaking about the current available and leading practices under the offshore program. This will lead into Ingvild's discussion on regulatory processes and history, but wanted to give you a little bit of background and about the project and where we are today. As we look at the SECARB offshore project objectives, a couple areas that come to note that led to our leading and available best practices for the offshore, and that's objective 1, looking at best practices, and then objective 3, collaborating with federal and state agencies to improve the confidence, but also looking at regulatory environments that need to be set up as we look at long-term geologic storage and enhanced oil recovery in the offshore environment. One thing that we did is we looked at what had been done in the past prior to SECARB Offshore, and there were several efforts that had been undertaken to look at best practices in the offshore. Starting back in 2012, SSEB and the Interstate Oil and Gas Compact Commission looked at a task force that reviewed existing regulations. Texas BEG prepared a report for BOEM on best management practices for the offshore, and that was done in, completed in 2017, and was a starting point. We also looked at the best practices during the SOSRA project, and one thing that we started looking at with the DOE and NETL was the fact that the discussion of best practices for the offshore environment when the U.S. has not had an offshore program is really not the best course of action. And so we started transitioning away from in the SOSRA project away from best practices and looking at what we deemed available and leading practices instead of best practices. The framework that we used was we kind of went back to the DOE, NETL onshore best practice manuals, and we compared those to the work that BEG had done in theirs, and the work that BEG had done on their best practices in 2017 lined up quite well with the work that was done on the onshore. We did notice the need for public outreach, but again, public outreach for offshore will be very similar to onshore with some differences in depending on where you are, state or federal waters. But again, the alignment was very well set up. The process that we're going through right now is looking at kind of available practices, and this is a process where we have gone in and we've looked at characterization, risks, monitoring, what is being done onshore, what is being done offshore, and how do those relate to the experiences we have for onshore projects, and how can we identify things that are similar, things that are different from the onshore to the offshore. And if we look at this kind of process, we have infrastructure components, so landside connections, transport and corridors. Some of these are very similar to what you would see in the onshore, and some of them are completely different or not even contemplated when we look at onshore as we start discussing platforms and seafloor connections. Well bores and wells, there are similarities, there are differences. When we look at geologic seals and barriers, a lot of the work that's been done offshore and a lot of the work that's done onshore is very similar, but there are differences, and we'll go into some of that as we look at kind of CO2 storage and utilization formation. So if we take site selection and then we expand into what we would deem kind of C16 as a cell, then we can look at what is available in the knowledge base right now for storage and utilization formations. And we look at site selection, and so then we can kind of go through and what's available onshore, and what available practices are there for onshore, and then how does that compare to the offshore. And what we've done here is we've kind of walked through, and if you go down to data requirements and costs, identifying data requirements to optimize modeling, conduct cost versus benefit analysis to determine value of acquiring new data. Comparison to the offshore, data acquisition costs in the offshore tend to be significantly higher. Data tends to be lower density due to higher cost. So, as we look at different areas in the offshore, you're going to have areas where you may have a lot of data available in areas that are, very, very active with EOR. But then, you start coming into, potentially entering into more risks because you may have more legacy well risk to worry about. So again, as we're looking at these various activities and various amounts of data, the additional data may come with costs, or the lack of data may provide additional benefits. So we're starting to also look at the various kind of triggers, if you will, as you look at what makes sense for a commercial scale EOR project and what makes commercial sense for a geologic storage facility. As we get through the process, we will start looking at leading practices. And this is where we will be relying on industry partners and international partners that have experience in the offshore environment, whether it's through well drilling and well completion to actual, offshore projects that have come to completion for EOR or geologic storage in Norway specifically. But what we've done here is we've started color coding areas of interest, if you will, for somebody if they were going to come and start looking at what would I need to know if I was going to go into an offshore geologic storage or EOR project. And as you look at things that are very similar to the onshore to very different to the onshore, and these codes will change as we get more and more information, but this is the general thought. So if you're looking at it from what do we need to be aware of if we're going to look at an offshore project, the things that would probably jump out to you right away are those that are going to be in red. And those are the things that you're going to need to focus on, the most, if you will, from the standpoint of the differences between the two projects. Those that are green are going to be very similar. So, as we look at long-term projects, these areas are going to become more defined, but the coloring may change as we go through the process. One of the things that's come out and is interesting and impacts the potential rate of regulatory development in the offshore is Executive Order 14008. And under 14008, this is tackling the climate crisis at home and abroad. Key actions include the fact that the U.S. will be rejoining the Paris Agreement, immediately begin process of developing the U.S. nationally determined contribution under the Paris Agreement. And it also directs the Department of Interior to double offshore wind generation by 2030. Now, a couple takeaways from my standpoint and a little bit of, kind of how I see this as potentially impacting the, offshore CCUS regulatory drive, if you will, from Department of Interior and BOEM is, if you look out there, I've not been able to find it, but the Department of Interior has not put forward any formal position regarding offshore CO2 transport and storage in the OCS. Again, I'm not able to find that. Maybe someone can direct me to that. But given the fact that they currently have a executive order from the president to look at offshore wind generation, doubling offshore wind generation, that's going to take up a lot of manpower at BOEM. The last time that Department of Interior and BOEM got involved in offshore regulations was back in 2008, 2009, 2010 timeframe when the PureGen New Jersey IGCC project was launched. And that was looking at capturing CO2 and taking it offshore about 70 miles and storing it in geologic formations off the coast of New Jersey. That project was canceled in 2011. So there is currently, again, as far as I can tell, no offshore OCS project that would drive BOEM to look at regulatory environment right now. I do think there are some positive factors out there for the offshore CCUS. Specifically, David Hayes recently named as Special Assistant to the President for Climate Policy at the White House. David, as Deputy Secretary of the Department of Interior during the Obama administration, initiated the initial consideration of CCUS in the OCS. So there is knowledge of offshore CCUS in the OCS. Also, under any scenario that you look at, CCUS is an important factor in all carbon management scenarios as you look at any type of 1.5 or 2 degree change under kind of the Paris Agreement. So there is going to be drive for CCUS, and that will be looking at the offshore. Also, there is positive movement in the states. I know I'm sure that BEG will be discussing tomorrow the recent announcement for offshore leases in the state of Texas for CCUS. So again, there are things that are positive for CCUS, but as I kind of read the tea leaves, it looks like BOEM right now is going to be focusing on offshore wind generation and may not have manpower or staff for a good bit of work in the regulatory environment for CCUS, just given that there is not a project on the horizon that may drive that. Remainder of BP1 into BP2 will be looking to expand the available and leading practices, continuing to build out these offshore practices and looking at existing infrastructure and regulatory obstacles. The material that we develop in the offshore for leading and available practices will be incorporated into the final report on assessment of legal and regulatory frameworks. And that leads into our next speaker. So I will step back and let Ingvild pick up from here.
Thank you, Brian. That was really good. And you left that on a very high note for me to follow. So just give me a second and I'll start sharing my screen here. I think now we got that. There we are. Hopefully you can all see my screen now. So thank you so much, Brian. That was a really good presentation, good overview of the best practices. I am going to talk a little bit on the Norwegian experience on implementing framework offshore for CCUS and how we've kind of done that gradually with different types of projects and how we have also done that gradually with different kind of frameworks inspiring us and also pushing us. So I have put up here a very brief agenda. I will talk a little bit about my involvement in this project because, well, Ken and Ben already mentioned on the regulatory stuff, and I know that Brian also talked about my involvement here, but it might not be natural to have a Norwegian lawyer being involved in a US project like this, where we are trying to figure out how to build regulatory framework offshore for the US. I will talk about the approach for the project and IOM Law approach. And further, I will use Norway as a case study to show you, as I mentioned, how we've experienced this over the last 25 years offshore. And I will give you a couple of bullet points at the end on what we intend to do in the next couple of years. So our involvement, I've put up a lot of pictures here to kind of just ease you into all of the technical legal stuff, but IOM Law is a super small boutique law firm. We have 3 employees. We have our main offices in Oslo, Norway, and we also have a satellite office in Tasmania, Australia, of all places. We have altogether more than 20 years of experience with CCUS issues, and we have a diversity on the formal background, having our degrees from Norway, Germany, Japan, and Australia, and also now ongoing in the US. So it's a little bit of varied background for us. And we have been involved in this project mostly because we can transfer knowledge from the Norwegian and European perspectives into the SECARB project and see how we can help out spotting some issues on the regulatory stuff. So this is our scope of work for this project. We are mapping out the regulatory analysis already been done because there has been a lot of done, as also Brian mentioned, on mapping the possibilities and the gaps and the hurdles in the US. We are doing a desktop review of all recent developments, both in the US and outside. We are comparing with other legal frameworks, like, for example, the Norwegian one, and we're testing them on the SECARB offshore case. And then we are forming some recommendation based on that. So that was just recapping what we are doing for the entire project. A year ago, when I was presenting for the annual meeting, this was my focus, talking about the previous work already done in the US. So we've kind of conducted a lot of those exercises while we are finding already very well funded studies, and we are drawing some conclusions and recommendations out from that. This, as I said, this is something that we will do throughout the project. So it's still going on, and it will be going on until the day we deliver the report, so that we make sure that we are not skipping any important steps and we're not skipping any important recommendations and observations by other experts, because we all need to pull in the same direction to receive and to deliver. This will be today's topic, talking about other legal frameworks and how we can take inspiration from that. And in particular, I'm going to talk about Norway, how we've experienced everything. And I'm starting out with a nice picture of Norway that has nothing to do with CCS. This is a non-filtered picture that I've taken up north during winter, where the sun is actually not rising above the horizon. So the lights are natural in this picture. I just want to give a little bit of commercial for Norway, so that when travel opens up again, you should go up here. And so over to the legal stuff. So brace for impact. I'm going to try to be gentle with you guys. This is a picture I often use, or an illustration that I use to illustrate how we are working with legal frameworks for specific topics. Although most countries are free to implement a regulatory framework themselves, most countries are also bound by international restrictions and regulatory frameworks. So like the Paris Agreement that has already been mentioned today, we need to make sure that the regulatory framework we implement internally is not in breach with that. Also, a lot of regions and countries have a regional law that they need to take into consideration. Norway is one of those, having the EU legal framework to take in as a part of their considerations when implementing frameworks. And then you have the domestic restrictions, like the constitution, that you have to take in to consideration. For the US, it's not similar, or it's not completely dissimilar either. You have the international legal framework, and you have kind of a dual system with the federal law and the state law. So there are kind of three different elements that you need to take into consideration the entire time. For Norway, I already mentioned there is a 25 years history of doing CCS offshore. Most of you have heard of Sleipner and Snøhvit. Sleipner kicking off already in 1996. And Sleipner did not commence as a CCS project because of climate change regulatory framework requiring people or companies to do CCS. It was commenced because the Sleipner field was producing natural gas that they were selling to the European market. And at that point in time, it was a required composition of that natural gas with a much lower CO2 contents than what was actually produced. So they had to strip the CO2 out of the natural gas, and due to an implemented CO2 tax offshore in Norway, it was decided to store the CO2 instead of venting it. And when the Snøhvit project came on board in 2008, it was a requirement from the Norwegian government when they provided a permit. So the project couldn't commence unless there was CCS involved. There has also been a couple of other attempts. This is a couple of them. Kårstø and Mongstad both were on their way to become full-scale demonstration projects for CCS in Norway, both in 2010 and 2013. We saw cancellations of those, unfortunately. However, the government retracted. They made a new strategy and a new regulatory framework for CCS. Both were launched in 2014. And then they commenced a new project for full-scale demonstration of CCS back in 2015, with a final investment decision made by the Norwegian government December last year. So, and this is the Longship project that most of you have already heard of. I will speak more on that in a few minutes. So how did we get started doing regulatory or implement regulatory framework to enable Sleipner to be commenced? I have listed here a few international instruments that we were bound by at that point in time. So not all of these would be applicable for the US. For example, OSPAR, which is a North European concept. But I know that the US is also not bound by the London Protocol at the moment. However, the starting point is not so unknown or unheard of for the US either. The starting point for Norway when they commenced the Sleipner project was that they were bound by the London Protocol, saying that the contracting parties shall prohibit the dumping of any waste or any other matter. And if you're looking at the definition of wastes, it is a very all-consuming definition, which will also imply that CO2 dumping is not allowed. So already there we have a small barrier that we need to kind of interpret our way around. And if you see here, we go into the national kind of interpretation and practice of the international rules, because there is an exception in the London Protocol saying that disposal or storage of waste or other matter directly arising from or related to the exploration, exploitation, and associated offshore processing of seabed mineral resources, it's not covered by the provisions of this protocol, meaning that the process of stripping CO2 from the natural gas process at Sleipner was not prohibited by the waste dumping prohibition in the London Protocol. Accordingly, the Norwegian government was able to use the Petroleum Act and regulations to implement the Sleipner CCS project. So it was possible to include the activities in the plan for development and operation and in the permit of the Sleipner license. And as Brian has already been talking about best practices, I don't need to talk a lot about that here, but I can mention that as part of this project and using the already existing regulatory framework for petroleum operations, there was already a set of HCC regulations in place, and there was also a set of best practices and standards in place that could be used to make sure that it was a safe and sound operation. And then later on came a package of CCUS related regulations from the EU. Most of you have heard about the CCS directive, I guess, regulating the safe geological storage of CO2. And then there was also a regulatory framework for emissions. So the ETS directive or emission trading scheme was implemented first, implementing then allowances that you have to pay for if you emitted CO2 of certain categories and from fixed installations. There's also an environmental liability directive, which very briefly told regulates the polluter pays principle, amongst other things. And then you have the CCS directive doing more of the administrative procedures of storing CO2. All of these instruments Norway has implemented as part of their ties to the EU through the European Economic Agreement. And we will look at how that was done, even though there was already a CCS or two CCS projects in place. Norway chose to stay with the path of having a separate regulation for petroleum-related CO2 storage. So Sleipner and Snøhvit, they are still storing CO2 according to the Petroleum Act and subsequent regulations, because the CO2 storage relevant to those operations were kept in those instruments. They did have to update their permits after a grace period. The regulation was, or the CCS directive was implemented in Norway in December 2014. And I think that during 2016, Statoil, or now Equinor, had to update their permits. Other CO2 storage, still offshore, even though the CCS directive allows for both onshore and offshore storage. Norway has stayed with only the option to store offshore. So all other CO2 storage, industrial CO2 storage, will be regulated or is regulated under the storage regulation and CO2 safety regulations. So that would be CO2, for example, captured from a cement facility and stored offshore separately, like the Longship project. And it can also be all other types of CO2. The only exception would be CO2 either stripped from petroleum operations and then stored, or for example, if you're doing CO2 EUR, they would also have to apply for a permit under the petroleum regulations. Regardless of whether you're doing CO2 storage related to petroleum or other industrial activities, you are bound by the Pollution Control Act, which will do a lot of the environmental liability regulations. And you would also be bound by the Greenhouse Gas Trading Act, which has implemented the ETS directive. So not all industrial activities that will be eligible for CCS projects and CO2 storage will be regulated by the ETS directive, but the ETS directive will apply for both a lot of industries onshore and for the petroleum industry offshore. There is also a separate regulation that controls the materials and documentation, which is an important part of the quantification and verification for safe geological storage. I'm going to touch upon standards and best practices as well, but very briefly, because this is something that Brian has already talked about in length. So this is just to say that Norway has done the same exercise, basically, that Brian has described, because both for the petroleum related CO2 storage as the Sleipner and Snøhvit project, as I mentioned, have already taken into use standards and best practices in place for the petroleum industry before CCS was even thought of. And there is a new set of CCS or CCUS related standards that are currently being developed. Some are published, some are still under negotiation. And those are the CO2, or those are the standards under the ISO Standardization Technical Committee TC 265. More information about that can be, if you want that, you can just email me and I can provide information. But the main point why the Norwegian authorities have chosen this path on regulating offshore CO2 storage, but also petroleum activities, would be some of these basic principles of technical standards of containing no patents rights and not kind of meddling in the regulatory criteria for example, frequency of reporting or criteria for decommissioning, et cetera, et cetera. They are not meddling in each and every regulatory public administrative principle. They are setting technical criteria, which often are better done by the industry themselves than having authorities kind of set the standard for them. So this is something that I totally agree with what Brian said earlier about looking for applicability for offshore CO2 storage in the US. I will talk a little bit about the Longship project very briefly, because I have also included in some backup slides some links for you guys. So if you want to do some reading on the Longship project or a couple of the other aspects that I'm talking about today, you can click on the links, and there are a lot of English or translated documents into English that you can read. So very briefly, this is the project that they commenced in 2015, and in 2016, the Norwegian government issued the feasibility studies based on that decision in 2015. They have gone through permits, final investment decisions, and also this year, the partners handed in the plan for, or they got an approved plan for development and operation. And the plan is to be fully operational in mid-2024. This is at least what is available online. And the good thing about this project is that now we get to test the regulatory framework that we have implemented. So the Sleipner and the Snøhvit project have been able to test the regulatory framework, how well a petroleum-related regulatory framework is adaptable to CCS activities. However, this Longship project will be the first demonstration project in Norway, which is purely regulated by the industrial CO2 storage regulatory framework. So now we are able to test how far the liability regime is developed, if it's good enough to regulate a project, if it's flexible enough, predictable enough, and also transparent enough. So a lot of the issues on, for example, cross-border collaboration with other projects, etc., we are able to test those now. So the point made by Brian earlier is very valid on having kind of projects to drive the development of regulatory frameworks. I will end today's presentation and by talking a little bit about the lessons learned and the way forward. And I think that this is lessons learned, observed with my eyes. So probably if the Norwegian governments were talking, or the Norwegian government was talking, or the project themselves were up here talking, they would pull out some other bullet points to show you. But this is, at least from my point of view, I think it is very important to point out that the thing that Brian mentioned on having projects driving frameworks is a very important lesson learned. It's very hard to provide a legal framework before you have activities. If you compare the implementation of regulatory framework for natural gas and CCS in the European Union, for example, there was an already existing industry for natural gas when they implemented the Natural Gas Directive, which made it possible for the European authorities to implement the framework to protect and continue developing that already commercial industry. But when they were implementing the CCS directive, it was more creating a framework for an imagined potential future industry. So having that in mind, it's difficult to kind of set all the standards to be fully aware of the risks and all the liability issues. So I think having these first demonstration projects will help us very far along to finalize where we should be. And I think also we get a good opportunity to test the performance-based requirements and how that flexibility serves both parties, both the private entities working on CCS and the public authorities, and dealing with the permits and dealing with the long-term liability issues. And I think that for the European Union, the EU ETS has been a very important economic driver for CCS activities, and also for Norwegian projects as such. We have the CO2 tax, as I mentioned, being a driver for both, especially Sleipner, but also Snøhvit. But currently there's also an issue ongoing in both the European Union in Norway related to negative emissions, having CO2 captured from air, for example, or from biomass. None of those CO2 volumes come with a financial incentives, which makes it maybe a little bit more of a dream than a reality to store those volumes yet. However, I know that both the Norwegian authorities and the European Commission are working on these issues. So hopefully we will find a solution there as well. So finally, way forward, IOM Law will compare and contrast the experience with from Norway with the US situation to see how much we can transfer and how much we can take from the Norwegian situation and build on. We will do some stakeholder engagement, talking to both camps, both Norway and the US, talking to public authorities and private stakeholders to figure out what can work. And we will test those findings and those conclusions on the SECARB project as it stands by the end of next year. And we will do this in collaboration, especially, well, the entire project, of course, but in particular, Advanced Resources International and Crescent Resource Innovation, well, and Brian, of course, then, because I think doing the recommended practices, the legal framework, and the financial and policies all together in one pot will probably make a stronger case for both the US and for recommendations in general. So that was me. I would like to say thank you so much for your attention, and I will be happy to take questions. I do have backup slides, as I mentioned.
Thanks. Do we have questions for either of the panelists? I wasn't seeing anything in either the chat or the Q&A, but if you have a question, feel free to speak up.
That's usually what happens when lawyers are talking. It's like, oh, yeah, she's done now. Now we can go home. Then I'll take the opportunity just to share the screen to show you the backup slides so I can show you what links are in there. So hopefully that could be helpful for not just the project, but for the participants in this conference. I have included here for you relevant documents that the Norwegian government and also the Norwegian Petroleum Directorate and several others have published online, which are both white papers describing here, for example, the Longship project and the process and the way forward, but also CO2 atlases and how they've dealt with the exploration permit, etc. So these might be some relevant documents for you to read. Unfortunately, this one is only in Norwegian. However, that is from the previous full-scale demonstration project. So if you stay with the Longship white paper, you will have plenty of good reading provided by the Norwegian government, Gassnova, and the private stakeholders involved in the project.
It looks like we have a couple of questions. One from Rob Finley. I don't know if you can see the Q&A. It says, will there be a different regulatory framework for Longship injection wells versus existing ones at Sleipner or Snøhvit? And then also Sue's hand is raised. So I think Sue has a question as well.
Yeah, I can start with the one from Robert, and then Sue can go next, maybe. So yes, there will be a different framework for the Longship injection wells because those are considered being industrial CCS or industrial CO2 storage. So unless the Longship storage site takes on CO2 stripped from petroleum processes, they will stick with the CO2 storage regulations outside of the petroleum industry. So this has important tax implications, for instance. So it's important to keep that separate. There's a question from Brian from Ken.
Yeah, I see the question on project insurers. I guess from the standpoint of project insurers, there's going to be a couple different levels that you want to look at that. And again, just from a very, very high level, the first one is going to be, and this is something that we'll be looking at from the standpoint of long-term liability of CO2 storage. One of the benefits that folks talk about in the offshore and they talk about in the in state waters is limited individuals for ownership. So in the OCS, the federal government and the states own the pore space. So a potential program setting up long-term liability where it would transition to the state or the federal government would be something that operators would probably be looking at as a requirement or a need for long-term storage post-closure. During the operations, the insurers would be looking at operational integrity. So that I can't really speak to right now. Again, this is new, but there is a long track record of individuals providing insurance to operators of offshore oil rigs, offshore drilling operations. So I think that the same players that are involved in there would be able to be involved in CO2 injection projects. But again, this is something that that the appetite at various insurer levels may vary based on operator, but also there may be the added benefit of looking at, when we start looking at ESG and being involved in projects that are carbon net positive, if you will, storing carbon. There may be interest in people participating in those projects, but again, I think it's going to be a different situation.
Sue, do you want to unmute?
Yeah, it's Ingvild. So since we have a real lawyer, I wanted to ask a lawyer question, and I know you don't know the answer, but I wanted to set it up for the future. That I think we have a mess in the U.S. waters, and seems to me there are two pieces to the mess that I'm not hearing anyone talk about correctly yet. One is the tension between the EPA, and the EPA can't rule in the federal waters because EPA is a congressional authorization, and the interior is cabinet. And the offshore waters are interior; it's a cabinet position. So I'm curious to even know what precedents or paths forward. How does BOEM need to make, and BSEE need to make do separate rulemakings, and when there are structures that are part fed, part state, there's going to be a cross jurisdiction issue that ought to be aligned somehow. And I'm not hearing any chat about what we're going to do about that. The second piece of my question is related, that the EPA's jurisdiction to manage the UIC program comes under the Safe Drinking Water Act for protection of water resources. Yes. And there aren't any offshore. So I wonder I'm not objecting or anything. I'm just worried about the durability of the decision that EPA made, whether it's going to get us into trouble in making progress, or whether someone should look at it, address it, and get it, so comments or suggestions, or am I crazy or what?
Well, you're certainly not crazy. To start there. Second, as you already assumed, I'm not able to answer this 100%, and I think very few would be able at this point, but it's certainly one point on our agenda, what we are going to do for the next year and a half. Because we are going to test the findings that we have from Norway and how it has worked offshore in Norway, and if it's in the European Union, to see if that is even applicable to the US federal waters at least, because it is because if you have the private ownership of land, etc., and you have the Safe Drinking Water Act, etc. in the US, I think having the same rule in state waters and federal waters would probably be difficult. So there needs to be some kind of collaboration between the public entities being involved in the permitting regimes on both sides. But I don't have a clear answer, but this is certainly an issue that that we are looking into. And I see that Melissa actually could respond to this. Oh,
yeah, but
she could have, yeah.
But she says she doesn't want to respond because it's not.
That's fine. Yeah, that's
but we
fine.
ought to let's take an intention in coming months to at least write a problem statement, at least lay out, and it needs to be from your expertise to say what are the natures of the problems and some of the possible mechanisms for resolution, and talk to all the EPA and BOEM, who I'm sure are already or would like an opportunity to talk to each other and just incubate progress so that resolution can be found, so we have certainty.
Yeah, and I think an important point.
Sorry, we only have about 5 more minutes to stay on track for our break, and there's a question from Darren. Do you see that in the Q&A?
No.
Yeah, now I can see it. But just to wrap up that sentence, I was going to say, just inspired by the comment from Melissa, it might be a good idea to set up a kind of an SPE format workshop for interested parties, so that one can discuss these issues without being recorded and being free to speak one's mind without yeah, any consequences for everyone who wants to participate. Darren, the comment here. US DOE is hearing a lot about industry interest in CCS in the Gulf of Mexico. Do you foresee industry pushing hard for establishing a CO2 storage regulatory framework for the OSC federal waters, and what agency should have regulatory jurisdiction? Yeah, I think I would have to answer the same thing here as I did for Sue, that this is definitely on our agenda for the next coming months. So I'm not sure if I'm able to answer that just from on the spot, actually. Sorry, Darren.
No, Darren, I think I think this question leads to you know, some of the stuff that I was kind of alluding to in my talk about my personal reading of the tea leaves, and you know, how we may see you know, without executive orders or without a push from higher up, it becomes difficult to get a focus without a specific project. If there's a project that's pushing and it's in the federal waters, I think then we can get a lot of movement toward you know, the regulatory framework. But as it sits right now, there are folks that are talking about things in the abstract, not necessarily talking to each other, and that's something that we could start pulling together. You know, either via conference calls or, you know, as travel starts opening back up again, small workshop meetings that would start addressing these items. But right now, you know, at the executive level, you know, wind generation doubling by 2030 is the focus, and I think we can get the focus on offshore CCUS as well at the executive level. Then you know, there might be a better chance of getting people to start talking about these projects in a more realistic form.
Yeah, I agree with you, Brian.
All right, so I'm gonna go ahead and say our break is starting, and we'll see you guys back in 5 minutes. All right, it's been 5 minutes. So our next topic is characterization of CO2 opportunities associated with CO2 EOR and saline reservoirs. We have 2 panelists. Our first speaker will be Matt Wallace, and he's going to talk about the characterization of offshore CO2 EOR resource potential. Mr. Wallace is a project manager with Advanced Resources International, specializing in unconventional oil and gas and carbon storage. Then we'll hear from Dr. Z at Louisiana State. He's going to talk about screening, ranking, and initial characterization of potential storage opportunities in Louisiana State offshore waters. He's a postdoctoral researcher at LSU Petroleum Engineering Department. He holds a doctorate degree in petroleum, and his current research focus is in the CCUS area. So Matt, if you want to go ahead.
Great. All right, thanks, Patti. Hello, everyone. My name is Matt Wallace. I'm a project manager with Advanced Resources International. I'm going to be talking to you today about some work we finished up at the end of last year, characterizing the offshore CO2 EOR resource potential. Brief introduction. CO2 EOR in the Gulf of Mexico could provide a really viable and important option for secure storage of CO2 with what we're calling byproduct production of oil. This presentation will outline the methodology we've done to characterize that potential in the Gulf of Mexico central planning area. We've used the CO2 profit model and reservoir data to characterize the technical potential for CO2 storage and potential oil production using CO2 EOR. And just for some context, out of the total original reserves in the Gulf of Mexico, the central planning area, which we focused on, holds about 87% of that total resource in barrels of oil equivalent. digging down into the central planning area of about 966 oil and gas fields. 241 of those are designated as oil fields, which we've focused on for our technical analysis. This is the basis of our analysis that we've started with here. Of these 241 fields, there's about 3.7 billion barrels of oil remaining, of remaining reserves left to be produced. So CO2 EOR could really provide a viable option for extending the productive life of these fields beyond the production of these original reserves. So what we've done is started with our central planning area oil resource, and we've screened these reservoirs to identify those fields that are likely viable options for CO2 EOR. First, we've divided the CPA into both shallow water and deep water reservoirs. The key distinction being shallow waters are in less than 1,000 feet of water, and deep water resources are in greater than 1,000 feet. I know that distinction can vary depending on who what data you're looking at, but we've used 1,000 feet for the distinction here. We've included some additional screening criteria to identify these viable CO2 EOR reservoirs. We've used an original oil in place of greater than 20 million barrels to identify those reservoirs that are large enough for CO2 EOR. We've also used API gravity of greater than 20 degrees and total reservoir depth, not including water depth, of greater than 2,500 feet. And these are to identify those fields that are likely going to meet minimum miscibility requirements for miscible CO2 injection. So what's the quote size of the prize that we're looking at to start with? Of the 241 oil fields, we've identified 168, and we're calling them candidate oil fields that include 570 reservoirs that are viable for CO2 EOR. And of the about 49.5 billion barrels of original oil in place, there's a remaining oil in place target of 34.2 billion barrels. That is the resource target for CO2 EOR. About 3/4 of this resource is located in the deep water candidate reservoirs, and the remaining 8.5 billion barrels of remaining oil in place is in the shallow water resource area. So what we've done is built a Gulf of Mexico CO2 EOR database of oil reservoirs that we've used to feed into the CO2 profit model, which has then determined our technical resource availability. And a little bit about the database. It's based on the BOEM reservoir sands data, and we've added several components that we need to run the CO2 profit model. And real quick, the database is divided into 6 different categories. First, a reservoir ID, including the oil field and the location, as well as the volumetric reservoir data, the original oil in place, and those criteria that we use to calculate that number. The reservoir production data, which is important for identifying the remaining oil in place numbers, and our well data, including current producers and injectors, as well as the shut-in producers and injectors that are in place in the fields. We include several different reservoir characteristics like depth and temperature, the API gravity of the field, permeability, and an important characteristic in this category is the Dijkstra-Parsons measure of reservoir heterogeneity that is important input to the CO2 profit model that I'll speak about a little bit here in a second. And finally, we include the CO2 EOR flood data that we calculate for each reservoir, which includes the fluid injectivity for water and CO2, as well as the minimum miscibility pressure and the injection pressure that's used for each reservoir. And finally, the pattern area, which we calculate based on an average flood time of about 25 years. A few reservoir data adjustments and other calculations that we make for the CO2 EOR database. We have calculated the oil in place number in the database, which is slightly different than some of the BOEM database OOIP values. And this is just to keep the reservoir data volumetrically consistent for the model. We've also adjusted some of the formation volume factor values just to be consistent with the reported gas oil ratio values that come from the BOEM data as well. And we calculate the oil and water viscosity data, which is an input to the CO2 profit model. Finally, we also calculate the reservoir sweep efficiency, and we use a reservoir oil saturation of 0.25, which is essentially a post-water flood value for offshore sandstone reservoirs. We've adjusted that value where needed, but this is sort of a standard assumption for the residual oil saturation for the sandstone reservoirs. Finally, Dijkstra-Parsons, it's, if you're not familiar, it's a value for reservoir heterogeneity, and it's important input to the CO2 profit model. The BOEM reservoir database does not include a Dijkstra-Parsons value. It can be a somewhat complicated value to calculate, involving measure of reservoir permeabilities. So what we've done is to estimate the Dijkstra-Parsons for the Gulf of Mexico reservoirs. We've assumed a bookend value of a low Dijkstra-Parsons value of 0.6 and a high value of 0.8. The Dijkstra-Parsons is the higher the value means a higher level of reservoir heterogeneity. Lower value means the reservoir is more homogeneous. So what we've done is correlated Dijkstra-Parsons with the primary and secondary recovery efficiency. And we've divided all of our candidate reservoirs into depositional environments. And we've assigned Dijkstra-Parsons based on the overall recovery efficiency for each reservoir. You know, lacking the ability to do really detailed calculations for each Dijkstra-Parsons value, we found that this was the best way to get you know, a relative value for Dijkstra-Parsons for each of the reservoirs. I'll note that we have three values for Horn Mountain, Petronius, and Cognac for our deep water Dijkstra-Parsons estimate. These values are from 3 case studies that we've completed with NETL as part of a separate study. And this is just to show that our correlation that we've used for the offshore database is relatively in line with the Dijkstra-Parsons values that we've calculated for these other reservoirs. So we've started with our candidate reservoirs, which, you know, fit the criteria for CO2 EOR. We've also done an additional screen for what we're calling the optimal reservoirs, which are likely to be large enough and provide a big enough target for CO2 storage and incremental oil recovery in the offshore that they would likely be candidates for CO2 EOR development. This criteria is applied for the shallow waters. The shallow water reservoirs, these fields have greater than 50 million barrels of original oil in place. And for the deep water reservoirs, these have greater than 100 million barrels of original oil in place. So comparing the optimal reservoir resource to our candidate reservoir resource, We still retain about 70% of the remaining oil in place of about 24.4 billion barrels. However, this resource is contained within about 30% of the 570 candidate reservoirs. So all of that to say that we have most of the resource within a lot fewer but much larger reservoirs. So as I mentioned, we have used the ARI CO2 profit model to calculate our technical resource availability. If you're not familiar with CO2 profit, it's a finite difference stream tube reservoir model. And we've used essentially post-water flood conditions for modeling the CO2 EOR technical resource. Not all of the reservoirs, of course, are under water flood in the offshore at this time, but we've assumed that CO2 EOR would commence in these reservoirs following water flood. So they're at post-water flood conditions when the simulation begins. Real quick about the CO2 profit inputs. Was there a question? Okay. The inputs to profit include well and pattern data, reservoir permeability parameters. Again, we use a 0.25 saturation for the sandstone reservoirs, fluid injectivity data, additional reservoir characteristics, and our injection parameters. I'll speed up just a little bit. As an example of our CO2 profit outputs, including water injection and CO2 injection data, and our fluid production. Real quick, just a calibration to our case study for the Petronius J2 stand. The offshore model that we've used for our technical numbers here, we're just showing that this model produced a very similar output to what we've used for the Petronius case study. We're storing about 138 billion cubic feet of CO2 in this case. So finally, our candidate technical resource availability. For the 570 reservoirs, we're storing about 4.4 billion metric tons of CO2 with byproduct oil production of about 6.1 billion barrels. This is equivalent to storing 400,000 metric tons per day for 30 years. Most of this is in the deep water resource, but there's about 1 billion metric tons of CO2 storage potential in shallow water reservoirs that are near shore and close to onshore sources of CO2. And finally, our technical resource for the optimal reservoirs, 3.1 billion barrels, billion metric tons of CO2 storage potential with 4 billion barrels of incremental oil production. And just for context, over 30 years of CO2 storage for the optimal reservoirs, this is about 235,000 metric tons per day, which is about 50% greater than what we're currently storing with onshore CO2 EOR at the moment. Lastly, a few factors for what might make an offshore CO2 EOR project viable. Reservoir depth is probably the main important component. Shallower reservoirs may have lower CapEx costs for developing CO2 EOR, so that's a consideration to keep in mind, as well as greater reservoir injectivity, which can allow for a larger pattern size, as well as fewer wells that need to be used within the project. And lastly, mobile oil is a big consideration to add to the project revenue and offset some of the development costs. So starting CO2 injection prior to the end of primary and or secondary recovery could be optimal, and definitely something that we'll be looking into. And with that, we're all finished.
All right, thanks, Matt. Dr. Z, can you share your screen?
Thank you, Patti, for the introduction. My full name is Mohammad Zulqarnain, and I am working as a postdoctoral researcher at the Louisiana State University. And today I am talking about the screening, ranking, and initial characterization of potential storage opportunities in Louisiana state offshore waters. And the agenda of my presentation is that first I will go over the area of study, which area we are covering in terms of the storage in the hydrocarbon formation and also storage in saline formation. Then I will go over the ranking and screening criteria that we used for the oil and gas field, and then how we identify the representative storage opportunities in depleted oil and gas zones. And also same type of criteria we used for the saline aquifer, and then we identify the representative saline aquifers in terms of the CO2 storage, and then what the future work we intend to do. And one thing that I would like to point out that we completed this work in like around December 2019. So this is the study area in terms of our storage in the hydrocarbon zone. So we are responsible to cover the state waters that are east of the western boundary of the Huma offshore district. So all these reservoir that you are seeing in the offshore state waters are shown. All blocks, there are approximately 160 total oil and gas fields, and we analyzed 125 of them that falls in this area. And as far as the saline aquifer are concerned, we covered almost all state water, except some area that are here, Eugene Iceland, I think so. And as far as the screening of the representative opportunities is concerned, we collected the total data production, oil produced, and gas, and then other parameters to see which oil and gas fields have more potential to storage and recovery. And one thing that I would like to mention is that the state database is not as comprehensive as BOEM, because we do not have that much data for the sands. So that is a little bit tricky part. So this map shows the overall production of the fields in terms of the million barrels. So, and then we collected when we map over the gas field, gas produced, gas is represented as a billion standard cubic feet of. And then this is the nearby sources, and they shown by their numbers are shown like how many megaton per year they emit CO2. And then these are the natural gas pipeline transmission pipelines, and the intention was that we can have some reference value for the distance, because pipeline distance will also be a criteria in terms of screening for the representative opportunities. So we propose that a hub can be here where where a lot of the transmission lines merge together. It is also onshore, so we take the distance from this hub, direct aerial distance of each opportunities, and then that is used in the ranking process. And as for the storage in the hydrocarbons is concerned, we use this correlation that was proposed by Savage in like 2017. It requires two additional parameters like the water production that is not reported in the state production data, and also it requires the estimation of the how you translate the production from the surface to the subsurface. So if we know the total cumulative oil, gas, and water production, we can go and for the oil, gas, and gas combination and oil reservoir, we can have some estimate of like how much CO2 storage volume in either in billion standard cubic feet or in terms of the million or in terms of the million tons or megatons. So for the water, because the water data is not reported to the state, so we just borrowed the data from the Gulf of Mexico, and then for the we use the lower value to be on conservative side so that we may not over-report it. So we use the gas fields because gas fields has less water production data, and we fitted a correlation for the partial drive, and that's how we estimated the if this much million standard cubic of gas is produced, how much cumulative water is produced from that Gulf of Mexico data from the BOEM. And this table shows the different parameters that we used in the ranking. For example, when the field was completed, started production, whether it is oil and gas field, its unit is still exists and it is still in use or in some kind of record there, and is this secondary recovery has been performed. If it is performed, then we preferred it and has a higher ranking. And then the number of wells also count, and then we use the major perforation intervals to convert the standard cubic feet to the reservoir cubic feet and barrels to the reservoir barrels or reservoir cubic feet. And we use the 4 criteria, criteria to rank these. One is the storage, how much cumulative oil, gas, and water was produced. So this translates to how much CO2 can be stored in these reservoirs. And then recovery, like in terms of the cumulative oil production and secondary recovery. We used a recovery of 0.1 of original oil place. So it means that if we have a larger production of oil, it means that we can recover more from that particular reservoir. And the development, we use the distance, platform age, and whether unit exists and whether secondary recovery has been performed to have like some development like cost or something similar. And then we use the number of wells to have a leakage risk. So the fewer wells will have less risk, and if there are more wells, then they have a relatively higher risk. With some of these criteria, storage, recovery, development, and leakage, and then normalized it to 0 to 100, so that the 100 is like the very good reservoir, and then the 0 is like a very poor quality. These are relative numbers. So this is how the data or the table is shown. It, for example, it shows for the few of the selected reservoirs, and it shows the oil, gas produced, recovery, storage, and development, and monitoring or leakage, and then its relative rank. And this is the map view showing the oil and gas reservoirs. And you can see that around hub 1, we have like a pretty good set of the fields. Here is the field with 100 rank. Here is 90, 77. So if we have something here in terms of the storage in the hydrocarbons, so this area seems to be like very prolific in terms of the hydrocarbon recovery and then the storage. Now we move towards the screening of the saline aquifers. Here I am showing the georeferenced USGS geopressure map. It shows that where the geopressure starts. So we use this like the criteria that we should not go into the geopressure region because we do not want to push the CO2 in saline formation against the formation that are already overpressured. So based on this criteria, we divided the whole region or the whole study area into 5 regions. Region 1 is mostly the Lake Pontchartrain, and then these region 2, 3, 4, 5, 6, and I just use the went clockwise. So region 1, 2, 3, they are just the numbering. They do not have like a one region preference over the other. And then we used for each region, we selected at least 5 well logs. And then within the 3,000 to 10,000, because in some of the regions, the geopressure starts from 11,000. So we say that 10,000 is a conservative limit. So we calculated all the thickness of the sands between 3,000 and 7,000. 3,000 is the supercritical approximation if we have the 0.465 psi per foot pressure gradient. And then we used the average porosity of 27%. And then in terms of the area, we use the polygon area that gives us the pore volume. And we use the 2% storage efficiency factor to calculate the storage capacity of these fields. We assigned the storage capacity to field by field instead of the like the offshore block number. So this shows the legacy oil and gas wells. So I am just showing it so that we can have an idea of where the oil and gas wells are and how they will impact the ranking, because more oil and gas wells, it means more leaking. In terms of we have to be, have some more preparation to address the leakage of well risk. So the areas that will have lesser number of wells will be having the a higher ranking in terms of the CO2 storage in saline aquifers. And like the storage in the oil and gas zones, here we have defined 3 parameters. One is the storage, which is the storage capacity estimate that I just have described, like 2% of the pore volume that we calculated. And in terms of the ranking development, distance, platform age, and whether the units exist, shorter distance, lower age, and existence of a unit results in higher rank, because if the unit has disassembled or the platform has disassembled, then we have to invest more. So that was the purpose of having a ranking in terms of development. And the leakage in monitoring wells, number of wells, so fewer wells have a lesser risk of leakage. And then we combine these criteria and then they normalize them between 0 to 100. 100 is the the most you can say that the good opportunities, and 0 is relatively not as good. So this slide shows the data of the fields. You can see that the field that has the highest hydrocarbon is also having a rank of 40 in terms of if we want to have the use the surroundings of that field for the saline aquifers. And the other fields are also shown, their rank is also shown, relative rank is shown in the last column. And this shows the ranking in terms of the where the fields are, which field has the highest ranking. So you can see that the fields that are in this lake area here, they have the highest ranking because the area wise, we have a large area. You can see that the state offshore waters are very in terms of the extent, they are not extensive, but here we have a large extent of the area available in the lake. And also there are lesser number of wells. So therefore, if we want to have saline aquifer storage, these offshore blocks perform better as compared to the ones here. But if we want hydrocarbons, then these are preferable. And in terms of the future work, our next steps, we have collected the representative logs for the highest ranking fields. And then in the future work, we plan to build the geological correlation based on the publicly available raster logs and collect or estimate the petrophysical data from the publicly available databases or sources, and create static and dynamic model for selected opportunities, and especially area of review determination for saline storage. And we also, as a effort of our carbon safe project, we also developed this very simple tool that if you know the porosity, permeability, and injection rate, you can estimate the storage efficiency factor for the saline aquifer. So we plan to use this tool along with the detailed modeling as well. So I think that this is my last slide. So I will welcome the questions and any feedback.
Thanks, Dr. Z. There are some questions in the chat. Some were directed at Matt, and it looks like he actually answered those in the chat. So if you want to look at the chat and maybe just answer, it looks like there's a question from Sue and one from Sean.
If you can hear me, I figured I would just ask the question. You assumed a storage efficiency of 2% for a geologic trap. I was wondering why that value is so low. That's more in line with what I would expect from residual storage, not you're looking at trapping CO2 buoyantly. You can theoretically create a column. You should be able to get to much, much higher storage efficiencies without overpressure, without leading to any major issues. So
yes, actually it is conservative value. So if you look at the correlations that I have shown, if we have high permeability, high thick sands, and the boundary conditions is like they are connected with the large aerial aquifers, then we have a storage efficiency that goes up to 10% or so. So we reported the lower value. And in terms of the other constraint, if due to the local faulting, the zone behaves as a closed zone, then your efficiency is only due to the pressure constraint is only up to maximum 1% or so. So these are the two extreme. One is the open boundary, one is the closed boundary. So we reported something in the middle, not very high.
Okay, even 10% seems low to me for a trap, but I would think you can get up much higher than that. But that's neither here nor there for now. We can talk about it later if you'd like. But 2%, you could say it's conservative. I think it's too low. It's not going to give you realistic values or
But
what you could expect.
You are talking. Yeah, I think that you are talking about injecting into a salt dome or something in which we have a structural trap. What I am giving is like in without the structural trap, if you do not have any like barriers there, and it is CO2 is allowed to go and you can push it as far as you can.
Well, I guess what I'm talking about too is where you can do any kind of pressure management. So if you're assuming no pressure management, then it's different.
Yeah,
and I guess you're assuming absolutely no pressure management.
Usually, I think that in the economics, pressure management may not be an option for the saline storage, especially.
Okay, that's it. And if you said that, I'm sorry if I missed it. But if you didn't say it, make sure you say that up front. We're assuming absolutely no pressure management whatsoever, and then then I would have recognized right away that that's why the number is so low.
I think that one question was like, is large-scale storage in salt dome or salt layers being considered as a viable option, or it is non-starter? I think that if you look at the salt dome structure and how many faults it creates, if it is not a hydrocarbon zone and we are not sure about its trapping or its like storage or its cap rock, then it will be a troublesome because most of the salt domes are highly penetrated. Not we have the well leakage, but we also are not sure about the containment in terms of how the saline aquifer will faults in saline aquifer will behave. So it all depends on the sealant feature of the faults. So if the faults are good and we are sure that it is not going to leak, then the salt dome provides a much better option as compared to the other flat horizons.
Okay, I see that Jack has his hand raised. Jack, do you want to unmute?
Yes, I'm unmuted. Just going back to the efficiency factor, and is that 2% essentially what is used in the same number that's used in some of the NETL saline formation calculations?
Yes, it is from the number 0.2% is from the NETL.
Oh,
data.
okay. Yeah. That is generally for gross sand thickness when you don't have a whole lot of information. So you're including a lot of shale and everything else in that. Whereas for really well characterized reservoirs, there are some higher efficiency factors in there that we generally use when we can get to a net pay type number for individual sand. So it is a matter of scale and how you're looking at it and how well resolved the data are.
Yes, as I mentioned, we just take the gross sand, whatever was in these between the thickness of 3,000 to 10,000. So we use that factor because we are not calculating the net sand thickness in this reservoir right now.
Oh, okay. And that makes sense. And in just the last discussion, that kind of jogged my imagination because I hadn't really thought about using the salt bodies themselves as storage for CO2, which could make a lot of sense because it's involved with a salt dome storage project in Alabama that is in one of the where they essentially dissolved caverns into the salt and they use it for natural gas storage, which is great for peaking. Essentially, Mobile can get natural gas when everyone's using tons of heat during cold spells and things like that. It can be delivered quickly. And I think that could actually be an important part of the EOR infrastructure is, if you need a lot of CO2, so if you have excess CO2, you can temporarily store it in salt caverns and then pull it out when it's needed, when the industry demands it. Because that was one of the discussions we always had with Denbury in some of our early experiments was, having a, assurance of a steady CO2 supply was actually really important to them in their EOR programs. So that may actually be an important part of the infrastructure.
So this next topic is going to be using machine learning to screen for representative storage opportunities. Our first speakers will be Jack Pashin and Keith Holdaway. They're going to talk about geologic screening criteria for CO2 storage and enhanced recovery in deep water reservoirs of the Mississippi Canyon area in the central Gulf of Mexico. Dr. Pashin is a professor and Devon Chair of Basin Research at Oklahoma State University. He's currently involved in a variety of carbon storage projects. And then Dr. Holdaway is an upstream domain expert and published author with degrees in geology and geophysics. So, Jack, go ahead.
Okay, great. Good morning, everyone. It's a pretty big team involved in this project from between OSU geology, engineering, and the business school, and Keith at the SAS Institute. And what we're essentially doing is looking at all the geologic factors that influence storage in the central Gulf within the SECARB area, and using the SAS VIA system to visualize and help screen the data. And I'm going to focus really on the geology and a lot of the relevant screening criteria, and then Xitong is going to take over after that and really get into the weeds, the VIA system, which I think is really an amazing resource for this. So without further ado, some of the big questions we're asking is, how do storage and enhanced recovery strategies apply to continental slope settings? So we're looking at the shelf and the deep water. I'm going to focus on the deep water today, just so we're not all over the place. And I think there are also some very interesting opportunities we have to think very hard about out there. And, what are the critical depositional, tectonic, hydrodynamic factors that we need to understand when developing storage strategies for salt tectonic settings? And then, what are the screening criteria we need to consider when developing deep water reservoirs for storage and enhanced recovery? So, our primary objectives are geological characterization, especially SED, structure and tectonics, hydrodynamic analysis, and then looking at just basic reservoir properties. We need to understand those. How good is the reservoir? How good are the seals? Things like that. Understanding the pressure regime is really critical out there. PT conditions can be pretty complex. And then ultimately use that to design the heuristic decision support system using VIA. So this is in the SECARB offshore project area. The map in the upper left shows the area and the available 3D seismic coverage offshore. And we're going to focus on the Mississippi Canyon and Vasca Knoll areas today, because that's where the bird foot of the Mississippi Delta is effectively out at the shelf margin. You get the easiest access to the deep water. And if anything's going to happen in deep water, that's probably the starting point. Plus, there are some very prolific reservoirs in that area. And also, we see about a little bit of everything you see, just about everything you see in the continental slope. So it's a really good place to get our sea legs and do some relevant work in this space. So if we go on a shelf slope transect, and we're looking at the continental slope, we're generally looking at shallow salt bodies on, essentially a Oligocene-Miocene detachment system. A lot of intensely faulted reservoirs there. But as we go onto the slope, we get broader mini basins. Everything is very intimately related to development of Lochthanous salt bodies. in the upper section. We're generally looking at Pleistocene type reservoirs, really not much older than Miocene in that part of the world. That's perspective. The Jurassic is down at the bottom of the section, but it generally is a pretty thin Jurassic, Cretaceous, Paleogene section out there. And so in the upper right, you can see we're really focusing on the deep sea fan systems at the top of the section. And something to keep in mind is you can drill 20,000 feet in that part of the world and not be out of the Pleistocene. So when we think of these deep sea systems, we're thinking of essentially developing turbidite fans and mini basins on salt. And for that reason, the Mississippi fan is an incredibly complex structure, not your typical turbidite fan where like the Bengal fan, which is bigger than the Indian subcontinent and just shows us a unified system of fans and channels. Things are a lot more complex in the Gulf of Mexico, and we get a lot of little tiny turbidite basins between salt bodies. And this is where these systems are well exposed over in the Keithley Canyon area and can trace a submarine channel in this area. And let me get the laser going. You might be able to see better. So here's a nice feeder channel running into some mini basins. These mini basins are low areas where the turbidites accumulate. And here we see a feeder channel and a bunch of distributaries from it that give us the fan lobes, much like option number 1 there. And eventually the system fills up and we tend to get more widespread more widespread fan deposits. So this is a seismic profile. It shows what type of heterogeneity we get in some of these deposits. And this is along the flank of a salt body near the Mensa field in the Mississippi Canyon area. And I highlighted the channels in yellow, and you can see that they're pretty well defined, and they tend to become deeper, better defined, more abundant upward in section, which actually just shows us progressive build out of the fan channel systems. And pretty much everywhere we get amplitudes within these systems, there are hydrocarbons present. Looking at a few well logs kind of gives us a feel for what the stratigraphy is like down there. And reservoir sands are shown in yellow, and they show up with extremely high resistivity because there's a lot of oil in the sands, and they tend to be separated by very thick mudstone sections. So, we look at this, you see lots of hydrocarbon accumulations, lots of thick sealing strata, and, in petroleum systems, we would refer to this as a supercharged high impedance system. In other words, something that is really charged up with hydrocarbons and has a lot of effective reservoir seals in the system. Here are some of the channel fills. We see classic, finding upward Christmas tree type log patterns in some of the sands, whereas others we get very blocky types of fills showing us that, pretty uniform sandstone, uniform grain size distribution throughout these things. And as we'll see a little bit later, the sand properties are pretty favorable in these types of settings. So when we think of the mini basins, we get between salt bodies, we can actually get a pretty continuous section from the Jurassic all the way to the Quaternary in yellow. So generally the Jurassic, Cretaceous, and Paleogene are in light gray here, and then the Neogene to recent sediment pile is shown in the dark gray and the colors above that. And here we have a big salt withdrawal basin, apparently subsided on the east or on the south here first, and then subsided later on the north, and the salt was expelled. We still have a little bit of the Jurassic mother salt here, and some allochthonous salt bodies shallow, some large tilt blocks imaged, angular unconformities imaged in the section. And in the central part of the basin, see that the system is partitioned with a conjugate horse and graben system and a series of tilt blocks, and a lot of these larger amplitudes that are imaged in the survey are hydrocarbon accumulations and things about them is that when we get into these faulted regimes, you know, even whether or not we have seals, the thing to be cognizant of is the faults partition the reservoirs. So I think of them as more partitioning risk and limiting the size of the area that can be drained and accessed by wells, as much as a lot of people look at them as potential leakage risks and things like that. This is the Mensa field, which is another partitioned one. It's a classic turtle structure. And on the south end, we catch the big Thunder Horse salt body, which extends from the Jurassic all the way up into the shallow sedimentary cover and actually has a huge overhang of the upper tongue. Below that is big subsalt field called Thunder Horse. But Mensa is a good example of prolific field. But again, the reservoirs tend to be pretty well partitioned by these conjugate fault systems. So being really careful about that is important. It's one of the things we want to catch in our screening. Or, you know, are we dealing with partitioned accumulations, or are we dealing with more continuous accumulations, and what's going to be easier to manage, and what kind of prizes are people going to chase first for CO2 EOR? Would we even consider anything for saline storage in this kind of setting? When you get into many of the mini basins, one of the things we deal with a lot are allochthonous salt tongues, and that's one of the key characteristics of the Mississippi Canyon area. And this one probably had a lateral feed. You can see that here we have a rollover type structure that's actually cut off with a big chaotic zone along what is interpreted as salt well, and salt may have migrated through here. The allochthonous salt body was actually overlying and overthrust, came up from the Jurassic. And then the younger sediment that postdates growth has a rojo structure in it. Essentially, it's a rollover horse structure is what that's short for. And in the withdrawal basin, we got lots of reservoir section that's truncated against the edge of the salt body. So they're probably sealed at the edges. And here where the section gets overthrust by the salt, we get upturned basin margins, and they're all sealed by the salt, whereas the younger beds tend to drape over the salt. And those are the things that can actually feed into some of the shallow fault system. I'll show you some gas anomalies associated with that in a little bit. So a lot of your very safe, secure storage is actually going to be in regions where we get these types of geometries where we can show salt flanking. It actually ends up being the biggest trap type volumetrically in the area. So looking at the Mars mini basin complex, the Princess mini basin is right here. Main Mars mini basins is right there, and a very complex history of salt intrusion. Oldest salt body is here, and actually as we go shoreward, the salt gets younger. So I see sequential replacement of salt, and that affected the mini basin development and things like that. And there are all kinds of structural panels. You know, here we're feeding into a fault, but if you get into this area, everything is dipping into a salt seal. So you can prioritize reservoirs that way, just looking at types of trapping mechanisms. Here we see a lot of big amplitudes. Those are hydrocarbon accumulations in there. And one of the things we can do, you know, amplitude analysis ends up being a very important part of this, and something that we're really excited about is we get the seismic rectified and everything. We're getting it over to SAS. They can actually do various supervised interpretation techniques. You know, we tend to do the old style, there it is, and map it out by hand. So there's potential for a lot of machine learning and automated applications here that we're excited about. But this is in the Mars field, and a lot of the hydrocarbon accumulations are gassy enough that they give us very nice bright spots. And some of these are down in the deeper section. There's oil and gas to great depth here, beyond where the amplitudes are immediately obvious. But there are also a lot of shallow gas anomalies, especially along these faults. A lot of these have shallow feed. The shallower hydrocarbon accumulation seems to feed into it as well, whereas the deeper ones don't. In fact, the sands often pinch out at the edges of the mini basins because turbidites like to go into the lows. But a lot of these are the major reservoirs that are the objectives for CO2 EOR and associated storage. So looking in the Devil's Tower, Tubular Bells region, we've done a little bit mapping of some of the mini basins. And this is a great example where we have a mini basin mapped out, a pair of flanking salt bodies. There's the upturned margin adjacent to salt and some structural highs here. It looks like, oh yeah, drill here on the structural highs. But when you actually look at the amplitudes, you realize that the hydrocarbon accumulation is really in a combination trap. It's on the flank of the structural high. And what this outlines is a fan channel system. And the red area is where the reservoir is really thick, and that's where the feeder channel is running through the system. So looking at these seismically in cross section and also amplitude mapping where we don't have salt above things is a real help for reservoir characterization and understanding the targets and their architecture. And one of the common things we see, this is in one of the Ursa structures, is we have a mini basin here and a big salt flank that's been a big upturned salt flank, and salt is overridden it, and edge of salt where it overlies the upturned flank is over here. And things get a little bit trickier there where the hydrocarbon accumulations exist and aren't obscured by salt. They're very clear. Well, there are wells in here, and but the amplitudes are entirely obscured by the salt, and that makes characterization a little bit more difficult. And yet these are a lot of major production and CO2 EOR opportunities there. So we have to look at things carefully and not rely too much on amplitude. Sometimes you just have to use good old structural geology and common sense to find the best opportunities. Lots of temperature and depth data, courtesy of BOEM out there. And so we've done a lot of work on the temperature profiles, pressure profiles. And this is the temperature depth data. Essentially, we're looking at just subseabed temperature differentials. We want to know what's going on in the sediment column, not the water column. So in terms of actual temperatures, you kind of shift everything relative to the seabed temperature. Things down there are a little bit warmer, so we want to get more meaningful geothermal gradients out of this. And you can see that most of the reservoirs fall between 9.3 and 15.2 degrees Fahrenheit per 1,000 feet. But there are some extremely cool values and some very warm reservoirs out there, especially adjacent to salt, because salt is quite thermally conductive. When we look at the pressure situation, we see everything from brine compensated hydrostatic conditions. So normal seawater is going to regulate the hydrostatic gradient shallow. At depth, we can get around to 30 and 35% brines. The hydrostatic gradient is much higher, it gets up to around 0.52 psi per foot, and that seems to give us a nice floor of pressures that are observed. And of course, the deeper you go, the more pressured things we get. This is an active supercharged petroleum system, and there's also a very significant component of overpressure related under compaction of the sedimentary column out here. So something to keep in mind is, a lot of the reservoirs are discovered in this state generally don't see pressure gradients higher than 0.88 psi per foot. They're approaching lithostatic. That's getting to really to frac gradient. And although I think we don't really see tensile failure of these rocks, it's really the faults that give us shear failure. And I think that not exactly going to go vertically through a seal, but this is what's driving a lot of migration and the fault related seeps that are well known in the Gulf of Mexico. So pressure depletion ends up being a big issue for injection in a lot of these overpressured reservoirs. So if they've undergone a lot of production, what kind of pressure decline do you have? How durable is that decline? And how do you operate in those environments? So that is something to consider, because ultimately, if in the native condition for an overpressured formation, you just don't have a lot of headroom for injection, whereas if you're close to hydrostatic, you have a lot of headroom. But then again, whatever the pressures are, you're not necessarily going to have to inject at very high pressure above that, because these are very porous and permeable sands that can transmit fluids very long distances without too much push. And again, the deeper you go, the higher the pressure gradients are tending to be. And this is just a regression plot showing subsea bed depth and the pressure gradients. So overpressure is toward the right of the diagram, under pressure to the left. So, no matter what depth you're at, you can get under pressure. This is just a different way of looking at the data. In terms of porosity and permeability, these are definitely Gulf Coast sands. Mean porosity in the focus area is 28.5%, which is exactly what we found at Kemper. Permeability is not quite as high. We have to settle for a mean of 295 millidarcies, but Darcy values are quite common. And that's largely because the sediment is finer grained and pore spaces are bigger, but more than enough permeability to deal with something that actually makes the reservoirs fairly easy to manage. Another issue is looking at the API gravity of the oils and considering the gas oil ratios. And based on the BOEM data, we're generally looking at oils that are within the window, or people talk about doing CO2 EOR, although there is kind of a sweet spot there. And I think opinions vary all over the place. And until you have good miscibility curves and understand the individual oils, it doesn't mean as much in terms of actually making a decision whether you're going to go or no go for CO2 EOR. But the vast majority of the reservoirs are, at least in some measure, in play for CO2 EOR and associated storage, which is a pretty obvious path forward out in this part of the world. So just some of the key observations is, there are certainly a lot of storage and enhanced recovery options in the upper continental slope. But, we're really dealing with supercharged high impedance turbidite mini basins with fan channel systems. That's a mouthful, but that mouthful is pretty much the story of the area. And I think EOR is a real key to getting things developed out there. I don't know that there's a whole lot of reason to be working at those water depths without EOR. So screening criteria include many aspects of depositional style, structural style, hydrodynamics, geothermics, basic reservoir properties. And we have lots of extremely high quality reservoirs, lots of thick reservoir seals, API gravity, pretty low gas oil ratios where API gravity is actually reported. And from what we're seeing there, a whole variety of salt flank traps, faulted anticlines, extensional tilt blocks, and combination traps that we have to choose from and screen among. So the faults partition the hydrocarbon accumulations. And I think that ends up being a really big screening criterion for here. And it's going to screen out some reservoirs, or at least put them in a different priority envelope. And of course, the pressure envelope, if anything, is what's limiting out here. You have to work at high pressures, and learning how to manage operations in this type of overpressure, especially at depth, is something that needs to be considered. And one of the things that needs to be considered is none of the fields out here have really been designed for EOR type operations, even water flood, and the wells can be engineered very differently than what we're used to seeing near shore and onshore. So there's a lot of technology hurdles, and I think a lot of innovative thinking that has to occur before we're ready to do these. But I think we need to ask the questions early and get some really talented engineers who say, yeah, I think I can see a way to make this work to get this all rolling. And ultimately, all these data we've collected are really well suited for the SAS via decision support system. And Xitong's going to take it from here. So stay tuned for his presentation. Thank you.
Thanks, Jack. Yes, we have one more presentation under the machine learning. and it's exploratory analysis of screening criteria for CO2 storage in SECARB offshore reservoirs using the SAS-VIA platform. We'll hear from Dr. Chakravorty, who is a professor of marketing analytics and director of the Master's of Science in Business Analytics and Data Science program at the Spears School of Business at Oklahoma State University. Mr. Hu is a graduate student in the Master's of Science in Business Analytics and Data Science program at the Spears School of Business at Oklahoma State University. And Dr. B. Kina is an associate professor and Harold Carson Chair in the Petroleum Engineering Chemical Engineering Department at Oklahoma State University. And so after we hear from them, we'll do discussion and questions.
Hello, everyone. Thank you for attending this topic. So the topic of our speech is exploratory analysis of screening criteria for CO2 storage in SECARB offshore reservoirs using SAS-VIA system. So my name is Xitong Hu, a research assistant in Spears School of Business, Oklahoma State University. So the advisors of this project are Dr. Bikina from School of Chemical Engineering, Dr. Chakravorty from Spears School of Business, and also Dr. Pashin from Beacon School of Geology, Oklahoma State University. Also, I would like to thank National Energy Technology Laboratory and also the SECARB offshore teams and SAS teams, their support for this project. A little bit of myself, I have a master's degree in geology. I graduated from OSU, and also now I almost graduated from the business analytics and data science with another master degree. After May, I'm going to graduate, and currently I'm actively seeking full-time work opportunity. So here is the outline of our project. We start with the project introduction and talk about the data sources that used in our project, and then I'm going to introduce the SAS-VIA platform, which is the primary analytics tools used in this project for data management and analyzing the geological data. And then we are going to talk about the results from exploratory analysis and the screening criteria analysis. And finally, we will conclude our presentation. The SECARB Offshore Partnership Project evaluates the potential CO2 storage opportunities in the mature oil reservoirs and the thinner reservoirs of the central and the eastern planning areas of the outer continental shelf of the Gulf of Mexico. And you can see from the top right here, the orange area shows the oil reservoir evaluation study boundary for, and then at the bottom right here, so here is the boundary for the sealand reservoir evaluation. So as we mentioned before, the major objectives of our project is evaluate the CO2 storage in the sealand formation, and also the depleted oil reservoirs, and also the current production reservoirs for enhanced oil, CO2 enhanced oil recovery. So we can consider several factors such as the geological information, reservoir properties, and the EOR, EGR informations. So all these data were collected from the BOEM data center, Bureau of Ocean Energy Management. And we also have there are 167 3D seismic surveys that covering most of central Gulf of Mexico that, as Dr. Pashin pointed out before. So these are from the USGS Marine Seismic Survey National Archive. So here is at the right, here shows the list of the data that we collected from BOEM data center. So the data include the sand table, borehole information, pressure data, directional surveys, and also pedal reports, velocity reports, and also the production data. So at the top list here, this data are in very well, all well formatted, are in Excel format, TXT format. So these are used Python to store these tables into the correct format and output as the consistent CSV files. And for the production data, we have the, so this is there are legacy PDF files that have the production records from 1970 to 2020. So we also use the Python to parse every tables out from these PDF files. There are over 6 million production records that has been parsed out for this over 40 years, over 50 years data, and then they are saved as CSV files and then ready to ingest into the SAS via system for the analysis. So here is the overall structure of the SAS via architecture. We can start look at the left side. So here shows some data sources that can be ingested into the SAS via system. So overall, SAS via is an AI analytics and data management platform that runs on modern scalable architecture. And then it can ingest the data from stream data, cloud, and popular databases. And all in our project, we just upload this data from our local system. So, and the key service of the SAS via system is this Cloud Analytics Service, CS system. So the data are ingested into this in-memory engine, and then the SAS via platform can provide different solutions for analyze the data, such as the analytics function, business visualization, and data management that we are currently using in this project. And this system can interact with different language and through the API, such as the Python. We can use the Jupyter Notebook to interact with the SAS via system, also with use the SAS original language and also other language and APIs to interact with the SAS via system. And so basically what we have done in our project by using this system is that we have collected all these geological data in the consistent CSV formats, and then we'll upload them into the SAS drive and load them into the CAS system, which is the Cloud Analytics Service in memory engine here. And then after loading them, we can use the function that provided by this SAS via system to do the visualization, analytics, and modeling of our data. So in this map, it shows the well locations from 2018 Atlas update, the SAM table, and we separate the wells into the shelf area and the deep sea area for comparing the geological characteristics between these two areas. So we use the water depths of 130 feet as the threshold of deep water and shelf, and also the shelf area is defined as the east of the longitude of minus 92.15 degrees, and the deep sea area is the east boundary is east of the minus 91. The west boundary is east of minus 91.9 degrees. So we can see overall. So here it shows the well locations from the SAM table. The brown color, it shows the shelf area well locations, and the green color shows the location of the deep sea area. So here is the temperature seabed subsea depths plot. We can see the left is for the shelf area and the right part is for the subsea area. We can see there is a difference between the correlation in these two areas. In the shelf area, the correlation very strong. It's almost close to 1, and it's statistically significant. And however, in the deep sea area, we see a more scattered or weak correlation between the temperature and the subsea depths. But the p-value is still significantly significant. And here it shows the pressure versus the subsea depth plot, and in the shelf. In both areas, we can see this black color guideline here shows the hydrostatic gradient, and the orange guideline shows the lithostatic gradient. So most of our the observations in these two areas are in between the hydrostatic gradient and the lithostatic gradient. And only a few observations that fall aside of this gradient envelopes are considered invalid and were excluded from this study. We think they are potential outliers. And here it shows the temperature and the pressure correlations, and we can see there is a strong correlation between the temperature and the pressure in the shelf area, and we can see the gradient seems to increase after this 200 Fahrenheit, and in the deep sea area, this correlation become weak, and there's more scattered pattern between the temperature and the pressure. So this results in a moderately strong positive correlations, but it's still statistically significant. Now let's look at this the pressure versus the oil formation volume factors in shelf and deep sea area. In here, when we compare these two correlation plots, we can see in the shelf area, the correlation is pretty strong and linear, but in the deep sea area, we see here after a certain point of the pressure, the oil formation volume factor that doesn't change anymore. So which means it exceeds the bubble point. So the initial oil formation volume factor doesn't change anymore, and all the gas are in the solution at this point. So yeah, as Dr. Pashin shown before, so here the porosity and the permeability, it shows pretty good correlations, and the permeability is in the log scales here, and we can see most of our sands are between 20% to 35% of the porosity, and the permeability is range from million darcy to dozens of million darcy to darcy level. So the range and is pretty consistent in these two areas. We can see the sand is relatively homogeneous and well behaved in both shelf and deep sea area. So in order to know, okay, what area to start to evaluate the CO2 storage capacity, so we first check the original oil in place in different BOEM field. So here is the oil in place volumes that aggregate by different BOEM field. So we can see here. So this is only for the deep water region that we currently targeted. And here is the top 10 BOEM field with the highest oil in place volumes. So the MC 807 field that has over 5 billion of original oil in place, and the the color is showing as the primary trap styles, and so it's associated with the flank traps associated with salt and shale diapirs, and we And following the second and third highest fields that associate with this faulted anticline, and others are associated with subsalt trap, anticlines, and turtle structure. But they are relatively less than this MC807 field. And here we showing the primary trap styles of the fields, and the left table shows the frequency of the fields in the deep sea area, and the right table shows the accumulated, aggregated oil plays in major trap styles. So we can see here the top three primary trap styles in the deep sea area are the flank traps, faulted anticlines, and tilted normal fault. So they all have pretty high oil in place volumes. But here is an interesting observation here. The subsalt traps have relatively less frequency compared to other trap styles, but the oil in place amount is pretty high in this trap style, so which means indicate a higher average oil in place volume. And the SASVAL platform also provide the visualization for the maps, and we can easily plot the data in this map view. And so here shows the location of the wells and colored by the major trap style. So then we can know, okay, what's the distribution of these trap styles in this deep sea area, and also this the size of the markers that shows the oil in place volume, and we can immediately find some well locations that associate with high oil in place volume and start to look at these areas. And also, so now we start with some basic screen criteria to screen the wells. So here is all the wells in the deep water, and then we start to add filters in this platform. SASVAL platform provide very user-friendly interactive filters, so we can set filters to filter the wells based on different criteria. Currently, we added the basic pressure temperature threshold for the critical CO2 storage, CO2 supercritical CO2 status, and also we added the permeability. It's at least 100 million Darcy, and the porosity is greater than 20% at the threshold that's selected from the RESA ETL 2016 study. So we can see that some wells have been filtered out, and with the continue of the study and adding more filters, so we can screen in the wells out and only left the high potential oils in the map, and for our to do the CO2 capacity estimation calculation. So in conclusion, there are several differences between the shelf and the deep water that have been observed through the temperature depth, pressure depth, and the oil formation volume factor plots. However, we can see the sand characteristics is kind of similar between these two areas, such as the porosity and permeability. And the most prolific deep water fields associated with the sand flank, sub-sand traps, faulted anticlines, and also turtle structures. And the top three primary traps in the deep sea area are flank traps, faulted anticlines, tilted normal faults, and they also have very high oil in place values. And also we observed that even though the subsalt traps have less frequency in the deep sea area, but they also have very high oil in place volumes and get our interest. And finally, the SASVAL platform is the major analytic tool we use in our project, and it works as an integrated platform for managing the geological data from different resources, and also provide very powerful data analytics to the visualization and modeling functions. Okay, that's all. So here is something about my current program, the business analytics and data science program in OSU. And if you need more information, you can contact Dr. C. And that's our of our presentation. Thank you very much. We are open to questions.
Okay, thank you. We have quite a few questions in the chat, and also there's one, I think, in the Q&A. So if the presenters could look and see which questions were directed to them and address those aloud, that would be appreciated. And I don't see, do you see anybody else with hands raised? I don't see anybody with hands raised right now.
Okay, I'm trying to look through and see. Oh, I know there was one about Q45 and EOR versus saline. And, for, Q45 definitely applies to both. Saline is, for the deep water, is a real tricky issue, largely because the cost of entry is so high. The $100 million wells are not uncommon, $100 million plus. So, how much of our installed base can we use? Can you even afford to drill new wells out there? So the oil is really the prize there. And that's generally the thing, we really see are the hydrocarbon rich zones. They do image seismically as bright spots. They contribute to the amplitudes. Let me see what other questions. Oh, approximate depths for 2 and 4 second two-way travel time. Generally, we're dealing with pretty low sediment velocities, seismic velocities, but generally, the 4 second range, you're down in the 15,000 foot range, maybe even getting up to the 20,000 foot range in some cases. Whereas at 2 seconds, you're relatively shallow, 5,000 to 8,000 feet. So a lot different from what I was used to dealing with in the Eastern Gulf of Mexico, where at 3.5 seconds, you're at 35,000 feet, much faster rocks out there. Okay, there's also a question about velocity pull-ups. And yeah, we did depth convert some of the things, especially what I showed that was mapped was depth converted, but that's something you have to be very careful of. Their velocity pull-ups below salt, and geometry changes when you actually apply a velocity model that accounts for the higher velocity of salt and sediment, especially at shallow depths, and becomes equivalent at a certain depth, and then you get the opposite velocity anomalies at great depths. The mother salt is actually slower than the surrounding sediment at depth. Salt has pretty constant velocity. But so that's something you have to account for. And clearly a lot of steeply tilted faulted tilt blocks, and places it's easiest to verify the dipping panels is where they're not overlain by salt. You do have to be very careful. Anything that's salt flank that's hidden underneath salt, you have to be very careful about properly depth converting through the salt and the sediment column. And things become lower relief once you do that below salt, that's for sure, once you take out the pull-ups.
I don't hear anyone, and I don't see any raised hands, so we could go ahead and break for lunch. We'll be reconvening at about 1:30.
All right, good afternoon, everyone. Thank you for joining us for the second half of today's presentations. I'm going to go ahead and get started. We're starting the afternoon sessions by discussing the technical parameters that influence CO2 storage. Giving the first and only presentation for this session, is Dave Riestenberg, Vice President at Advanced Resources International, and Oudinot, Project Manager, and Jalali, Senior Consultant, both at Advanced Resources International. Together, they will talk about parametric studies to assess technical prospect feasibility for offshore CO2 storage. Take it away.
So, thanks everyone for hurrying back after a relatively brief lunch here. So what the three of us are going to talk about, and majority will be Ann and Jalal to talk about the modeling and simulation work they did on this topic of a parametric study to assess, the feasibility of offshore CO2 storage. And of course, we'd like to acknowledge support from U.S. Department of Energy through the SECARB Offshore project for this, and technical management by the Southern States Energy Board. So, the goal of this little study, this little component of the bigger SECARB USA effort, was to review some of the key parameters that have the largest impact on CO2 plume size and CO2 EOR performance in offshore reservoirs. Obviously, these kind of fall into three categories. We'll call them tectonic or structural categories. Reservoir dip and fault block size. Reservoir properties, the one that we were interested in mostly, was in permeability. And then development strategies. So the well field, it should be layout. The well field layout, whether or not the field in the case of EOR reservoirs, EOR candidates, has undergone water flood, and then the subsequent CO2 flooding strategies. And so understanding these parametric values for Eastern Gulf of Mexico reservoir hopefully help us facilitate, one of the big goals of SECARB USA, which is locating successful offshore CCUS projects. And, we're looking at them in this application in terms of plume size, CO2 stored, and in the case of EOR, of course, oil recovery. Pretty simple outline. I'll just introduce things briefly and talk a little bit about how we define the parameters. Turn it over to Ann to talk about the computational numerical flow simulations that she did. And then finally, Jalal will discuss the reduced order model development that he did. So our main data set that we used to determine the ranges of the ranges within the parameters that we evaluated was the BOEM SANS data set. I think this is the 2019 version. And we screened it geographically for those that fell within the SECARB USA region. So, suffice to say that's Central and Eastern planning areas. That ends up still being over 5,500 SANs that are within our area. And you just could see a few histograms there that show, on the x-axis, the range of values of that parameter, and on the y-axis would be the number of sands that fall within those individual categories. Kind of interesting to post it like this. You could see in permeability, for example, you've got kind of a nice statistical distribution of permeabilities, but then you've got, a handful of reservoirs that are over 1,500 millidarcies, or 1.5 darcies. But the rest of the parameters are varying, I think, predictably, and so we felt good about the statistical variation in these this data set, and use that to in part to determine the ranges that we evaluated in the simulations. And just this probably isn't really even necessary if folks were able to watch some of the previous presentations, including Jack's, but just to give a bit of an onshore analog to what we're looking at offshore, we just did a little bit of a review of the Hastings oil field, which I think a lot of folks have probably heard of. It's not too far from Houston. It's a onshore salt core dome oil field that is currently under CO2 EOR operations. And the reason I say that, that may not have to do too much review of it, is it what we put it in here to do is to illustrate that these reservoirs or these fields are often individual fault blocks of varying sizes, varying dips, and in some cases even varying reservoir properties. You saw that jump out if you saw Jack's presentation, though, of some of the offshore fields that are also have salt influence structures. But again, Hastings has, specifically talking about the West Hastings field, has a handful of structural traps. Currently, the field's, I think, being developed in 5 fault blocks. In the image there is A through E, all individually. With in the field again is under EOR flood now, with individual flooding strategies, injectors, producers, etc., and timing for each fault block. So they're all kind of acting as individual fields in a way. you know, just some of the findings that have come about as a result of that is, you know, that faulting at Hastings required obviously more careful planning for CO2 injection in the EOR application, but you know, those structural traps aid in repressurization of the reservoir and containment of the injected CO2. And so kind of keep that individual fault block concept in mind when you see Anne's slides on reservoir simulation. And so with that, I'll turn it over to Anne. And, you know, I can just keep toggling through the slides, Anne and Jalal, if you guys just want to tell me when to advance.
Yes, please, that would be great. Thank you, Dave. So you can move on to the first one, please. Thank you. All right, so in order to further understand how the variation in the geologic settings may impact the storage resource, so what we did is that we did conduct a sensitivity analysis, which is what I'm going to cover now. So we took into account the sound properties that Dave just presented, and we built a series of synthetic geologic models. For the modeling, we used computer modeling group GEM Reservoir Simulator, which is a fully compositional 3D flow model, which is highly capable of simulating the injection, the transport, and the fate of the injecting CO2. So the picture that you see here is a 3D representation of the model. So it is a 20-foot thick sand, which is approximately the median thickness for the porous reservoirs in the Gulf of Mexico. It has a constant porosity of 30%, which is consistent with the numbers that Jack presented earlier this morning. And we assume a constant dip across 10 miles of distance. So remember what Dave just talked about. So to represent a fault block, the faults were implemented at the top and the flanks of the reservoir, and while the bottom of the reservoir will behave as a large aquifer. For modeling purposes, so we assume the injection well to be completed in the middle of the fault block, as you can see here. We injected over the full thickness of the reservoir, so the 20 feet, with a maximum injection pressure of 6,000 PSI, which is about like 0.6 PSI per foot, for a period of 20 years. And in addition to that, we imposed an injection rate limit of 50 million cubic feet per day. Next slide, Dave, please. Thank you. So the parametric values that were selected to cover the range of the properties that exist in the offshore. So for each property, we took into account what we call a mean or an expected value, a high value, and a low value to quantify the impact that they would have on the injection volume, the plume size, and the resultant storage efficiency for 20 years of CO2 injection. So to start with, for saline storage, we investigated three main parameters. And those were the depth of the formation, the permeability, and the distance between the fault. The histogram that you see on the left here that Dave has just presented earlier shows a log normal permeability distribution in the Gulf of Mexico, and which has a median value of about 250 millidarcy. So once again, consistent with Jack's number, a low value of about 50 millidarcy and a high value of 1,000 millidarcy. So because we have fixed the formation thickness here, permeability is a very important parameter because it will control the injectivity. To explore the depth of the structure, so three cases were selected to look at little to no dip, so 1 degree, moderate dip of 3 degrees, and then a dip within the range of the onshore salt influence structure of the Hastings fields that Dave mentioned earlier. So we went up to 7 degrees. And finally, through the implementation of lateral faults, the project can explore both the variation in the fault block size as well as the well spacing. So for lateral fault distance, we explored 1, 5, and 10 miles. Next slide, please. Okay, so let's look now at the result for each of the three sensitivities. So we're going to start with permeability. So when we varied permeability, we fixed the dip, which we kept at the mean value of 3 degrees, and the full spacing was fixed at the mean value of 5 miles. So the figures on the left here shows the CO2 plume at the end of the 20 years of injection for the low, the expected, and the high plume cases. So just a reminder, like the reservoir is dipping to the right of the picture. And as would be expected, of course, the plume size increases with the permeability as more CO2 is being injected. For the low and the medium cases, you can notice that the plume is nicely centered around the injector, while it's clearly moving up dip for the higher permeability case. And it should be noted that actually for the high permeability case, the injection rate limit that I mentioned earlier, that 15 million cubic feet per day, was reached for the first year of the 20-year injection. The figure to the right shows the cumulative CO2 injection and consequently the cumulative CO2 stored, which you should increase with permeability. So if you look at the average case, which is the red curve that we call our base case, so a 3-degree dip, a 5-mile spacing, and a 250 millidarcy, we're showing that you can store up to 150 BCF of CO2 with that configuration. Next, please, Dave. So moving on now to the impact of the formation dip on the storage. So for that case, now we fixed the perm at the average value of 250 millidarcy, and the full spacing is 5 miles. So the figure to the left, once again, shows the CO2 plume after 20 years of injection. And as you can see, the impact of variable dip is almost inexistent. Even though if you look on your right at the cumulative injected volume, there is slightly more CO2 injected with increasing dip. And the modeling shows that the CO2 plumes goes from a round shape to a more oval shape and is migrating up dip with increasing dip, obviously. Next slide. So the impact of full spacing. So for this case now, the perm is still fixed at 250 millidarcy, and the dip is our median of 3 degrees. So as you can see on the top left picture, so the full spacing at 1 mile, the CO2 injection is limited because the faults are closer, so you have a smaller spacing, and which is creating a smaller and a much more compressed plume. With increasing spacing, more CO2 injected, and the plume extend. And you can see on the right side the impact on the volume of CO2 that can be injected. Next, please. So that slide is a summary table of what I just talked about. So you can see the volume of stored CO2 for the different cases that we just mentioned, our base case, and then the variation with dipped, full spacing, and permeability. In addition, we also include an approximate size for the CO2 plume. And of course, like the highest plume is the case with the highest permeability, so which has the biggest impact on the plume size. Next, please. So moving on now to the EOR fields. So in order to make sure we're properly modeling our offshore EOR fields, we looked at results from previous studies, and we used those as analogs to ensure that the recoveries that we were getting were consistent with actual field data. So we used the Petronius field, the Cognac, and the Horn Mountain fields. The actual primary plus secondary, so which is primary plus water flood, oil recovery for those fields range between about 30 to 50%. And for the cases that we build here, our primary plus secondary recovery range from 38 to 49%, so which is within the range of the actual data. The picture that you see here is a 3D view of the model with a 5-mile fault spacing. The green area shows the oil saturated area, and the blue area is the aquifer. For all the cases, we have an initial oil saturation of about 80%, and we used the oil composition for the Petronius field. The list on the right, which I'm not going to read, but shows the 9 sensitivities that we run. So similarly to the saline case, the simulation investigating the impact of dip and fold spacing, while we decided to keep the permeability constant at the average value of 250 mRC. And in addition, we, because it's in EOR, we investigated several development scenarios, which were answering questions such as, well, what if we were not water flooding before EOR, or what if we started CO2 injection right away instead of delaying it? What if we're switching the producer engine injector and doing like a bottom-up versus a top-down injection? And what if we move the injector around and see what that impact would be? Next, please. So I don't have time to go through all the results for all the cases because there were a lot of them. So first, regarding the variation in dip and in fold spacing, the results are actually quite similar to the result that we have for the saline storage. So the only difference might be that as dip increase, in the case of CO2 EOR, the CO2 moves further and faster, and hence, because now we have production, more CO2 is being reproduced, and so consequently, we're storing a little bit less. Otherwise, the results are similar to what we saw for the saline storage. So the 4 pictures that we're showing here are the CO2 plume for the 4 scenarios that I just mentioned. So the first one on your left is the water flooding versus the no water flooding. So as you can see, when no water flooding occurs beforehand, as the reservoir pressure is much lower, much more CO2 can be injected and stored. And as you can see, the plume is much bigger. So the CO2, at the elevated CO2 saturation, if you look at the scale, anything that in the yellow-green range is about like 60–70% gas saturation there. What we did after that is we kept that case with no water flooding, and instead of delaying the CO2 injection, we started CO2 injection right away. So that's the second picture here that shows the delayed injection versus the immediate injection. So more CO2 is being injected when we inject right away, but we still inject it for the same duration of 20 years, of course. However, so it's hard to see it on the picture here. Basically, the CO2 sequestration in both cases is quite close because when you start injecting right away, obviously more CO2 is being reproduced and recycled. So in terms of volume of CO2 stored, it's quite the same. What we did after that is that, so I'm sorry here, I mixed up the pictures. So if you look at the fourth picture on the right, we decided to move the position of the injectors down dip. For the first picture, base case, then we move, you can follow the arrow and see how the injectors are being moved down dip, basically more and more into the aquifer. So when we do that, when moving the injectors into the aquifer, less CO2 is being injected due to the incompressible nature of the water. But however, when the wells are positioned further away from the producer, then less CO2 is being reproduced. And as a consequence, the volume of CO2 sequestered are about the same in the 3 cases. And the last thing that we looked at was switching the producer and the injector, and looked at top-down versus bottom-up injection. So this is the 3rd picture here. So if you look at it, we simply switch producers and injectors. So one thing that we had to do, though, just to make sure we were comparing apples to apples, that when we moved the producer closer to the aquifer, we had to make sure that we were keeping the same recovery values in terms of oil recovery. So we had to move the producer a little bit up dip so they were not too close to the aquifer. More CO2 is being sequestered when we look at the bottom up versus the top down. So the CO2, if you look at the saturation map for the bottom up, the CO2 moves to the aquifers and stays in the aquifer, and hence is not reproduced. So more of it is being stored. Next, Dave, please. So and finally, so a summary of the EOR cases. So this is a summary of the 9 cases that we just talked about. And so you can see on that table the incremental recovery in terms of EOR, as well as the net CO2 sequestered for all the different cases. And so that's it for me. Now I'm going to give Jalal the next section. Thank you.
Good afternoon. My name is Jalali. Hopefully everybody can hear me. I'll talk about the reduced order modeling section of this project. If you go to the next slide, please, Dave. So the objective of the proxy model or reduced order model was to predict the CO2 plume size in a saline formation CO2 storage project in order to develop to have a fast and reliable model that is built on numerical reservoir simulation. And the benefit of that, in addition to it being fast and having reasonably good accuracy, is to make you free from kind of an expensive or a numerical reservoir simulation, and have it more portable and more accessible to people to use. And also, these response surface models are essentially just algorithms that you use physics-based data, input and output data, to tune them and train them to reproduce the outputs that you get from, in this case, a reservoir simulator model. Next slide, please. So the model setup is essentially the same as the saline model that Anne had. It's a fault block in an offshore setting. We inject CO2 through an injection well in the center of that fault block. It's a 3D numerical reservoir simulator gem that has been used to run the CO2 injection scenarios. We've assumed a range of possible values for a few of the parameters, mainly the formation dip, formation permeability in the horizontal direction, and the fault block width. And the ranges that you see here are similar to the ranges that Anne had assumed in her studies. And CO2 injection is occurring through one well. We've set a maximum bottom hole pressure of 6,000 PSI. In this phase of the study, the way I modeled or trained the algorithms was to use the injection volume as an input. We realized that this should be probably a more of a two-step process, where your first step is to have a model that predicts the injection capacity of the model, how much you can inject into the system, and then use that as an input for the next model, which is to predict the CO2 plume size. But at this point, we're considering that as an input into the model. Next slide, please. We looked at several algorithms. They're listed here, starting from a simple linear regression, adding some more complexity or different regression problem algorithms, including neural nets and decision trees and random forests. So we tested these, and then out of these, we picked the best model that gives us the smallest error in terms of predicting the CO2 plume size. Next slide, please. So the workflow is pretty straightforward. We have a data set of 1,000 simulation cases. Using that base case that I had from the numerical simulation phase, where Anne did, used Latin hypercubes sampling method to generate 1,000 cases to make sure that we're covering the whole parameter ranges in a kind of a uniform fashion. To pick the best model, we did a cross-fold, k-fold cross-validation, and it's essentially a methodology to make sure that your training or your picking of the best model is not by luck of picking or not making it dependent on a portion of your training data set. So we cut that 1,000 simulation case data set into 5 sections, and each time we take one of those sections of the test set, and the rest will be used as the training. The average of those errors will be used as the average of the error of that specific algorithm. And then the model, the algorithm that gives us the lowest error is the best model that we pick. Then we go into the next phase of using a 70-30 split for training and testing the data set to train the algorithm. And then the last step would be to go into forecast and prediction. And we have a blind data set of 7 cases where I'll show you the results of the algorithm that we've trained here and compared with the CMG results. And just the last item is that we normalize the data using the min-max scaling method to make sure that the scale of the input parameters doesn't impact the model training. Next slide, please. We did a feature ranking here. We know that we're dealing with only 4 parameters, but it would be interesting to see what is impacting the CO2 plume size the most. Obviously, the amount of gas that is injected into the system has the highest impact on the plume size, but the next is the permeability, and the dip angle has a lower impact than the 3. Next slide, please. So as I mentioned earlier, we did the cross-fold validation, and we found that the multi-layer perceptron, it's a neural net with 2 hidden layers, gave us the least amount of error. You see the average cross-validation error on the bottom left table. And then we use that neural net to do the next training and then go into the prediction. And the table on the bottom right is a summary of the blind set prediction. What you see in the numerical model plume row, that's the results from CMG. I'm showing them in square miles, but they're essentially the same as I believe some of the cases that Anne had ran and showed earlier, but they were showing in acres. And the MLCO2 plume is the machine learning predictions. And you see that the highest error is 10%. It's a reasonably accurate model. Next slide, please. So in conclusion, for this presentation, representative Gulf of Mexico structural, reservoir, and development parameters were evaluated to determine their impact on CO2 storage, and these impacts were modeled. As the parametric value for fault block increases in size, more CO2 can be sequestered for both saline and EOR cases. The CO2 plume size extends. For both saline and EOR, changes in parametric values for dip do not have a significant impact other than the shape of the CO2 plume, which tends to elongate as dip increases. For saline aquifers, changes in permeability have the biggest impact on CO2 plume size. In EOR modeling efforts, they suggest that it would be beneficial to start CO2 injection early in the life of the field for a substantial increase in oil recovery. And lastly, a reliable proxy model was developed, which can be used to perform uncertainty analysis at a small fraction of the time required by medical reservoir simulation. Thank you very much.
Great. Thank you, Dave, Anne, and Jalal for that presentation. We do have one question in the Q&A. The attendee asks, how did you get the 1,000 data points for the CO2 plume size prediction? Was it actual simulation results or some other method to infer the size?
How did you get this 1,000 data points? Well, we got the 1,000 data points by running the simulation 1,000 times, generated 1,000 different realizations, different parameters within those ranges, ran the model, the CMG numerical model, and got the CO2 plume from CMG, and the input-output data set was used to train the neural net. So yes, we did use the numerical simulation results to have the CO2 plume as the truth CO2 plume size, and then we trained the machine learning algorithm to give us that prediction. If the question is why you picked 1,000 data points, that was, we started at 1,000 and we realized that that's a good enough number of cases to let us train the model.
Okay.
So we stopped at 1,000.
We have one more question from Curtis Oldenburg. Would anisotropic permeability give larger effects due to dip? That may be a question for Anne.
Yeah, yeah, I'm here. Well, yeah, it would. Yeah, if you have higher permeability in one direction, it would affect the definitely the shape of the plume. So it would be more oval than round, which is the way I presented it now, which was supposed to be isotropic in that case. But yes, that's correct.
Great. Well, with that, we're going to move into our next session here. We'll be discussing evaluating infrastructure options in the offshore environment. Our first speaker will be Hanna Downie, System Engineer for Aker Solutions. Hanna will be talking about enabling CO2 EOR with subsea processing. After Hanna, Anne Oudinot, Project Manager at Advanced Resources International, and Angus Marshall, Energy Transition Engineer at Pale Blue Dot, will discuss establishing CCS CO2 EOR infrastructure in the Gulf of Mexico. The floor is yours, Hanna.
All right, so yes, my name is Hanna Downie. I'm a system engineer with Aker Solutions, working on subsea compression projects. So yeah, our involvement in SECARB has been to design a subsea processing system capable of separating the CO2 from a well stream and directly re-injecting it for EOR. So yeah, I'll just briefly describe who we are and what we do in subsea processing, and then I'll run through the system that we designed for SECARB. Okay, so we deliver integrated solutions across the life of an energy asset, and so we work from early concept through to decommissioning. Historically, we've been quite focused on the oil and gas industry, but we're increasingly working on renewable and low carbon solutions, which of course includes CCUS. So we design and build subsea processing systems based around a few key building blocks. So being gas compression, boosting, separation and injection, seawater treatment and gas treatment. And we often work with clients from early concept development phases throughout technology qualification to develop new solutions to enhance field recovery. So in 2015, we delivered the Åsgard subsea compression station. And this project really pushed the boundaries of what was considered possible subsea. And this is relevant for subsea processing for CO2 EOR because it relies on the same technology as was qualified and delivered for Åsgard. And from the image on the right, you can see the scale of the equipment that's installed. Okay, so these are some of the biggest challenges that we see to realizing full-scale offshore CO2 EOR. So firstly, there may be insufficient CO2 available and or a lack of infrastructure to transport that CO2 to where it's needed. And because existing facilities usually haven't been designed for future CO2 EOR, that means that space and weight is usually extremely limited on the topside facility, and existing infrastructure may not be sufficiently corrosion resistant. And brownfield modification of these facilities can be extremely costly, sometimes prohibitively so, both in terms of CapEx and production deferment. So to minimize the impact on existing facilities, a subsea pre-treatment system can be introduced to remove the bulk of the CO2. And this leaves a very low CO2 concentration to be processed by the existing asset. So we see that the footprint of a subsea system is generally relatively small compared to a new topside CO2 handling facility, and only some power and controls equipment needs to be hosted topside. There's also the potential to debottleneck the topside process, since lower volumes need to be processed by the topside facility. And there's also benefits in terms of HSE risk and deferred P&A cost. So our objective was to provide a high-level system design and cost estimate for a subsea-based CO2 EOR system in the Gulf of Mexico. And to do this, we created a representative case that could be applied to identified prospects in the Gulf of Mexico, rather than designing a specific solution for a specific field or asset. So we used the production profile from the Horn Mountain field, which is provided by Advanced Resources International. And then we just selected 2 cases from that production profile for system design and sizing, which was years 25 and 29, which corresponded to a CO2 content in the well stream of 37 mol% and 44 mol%. We also designed the system for deep water at 5,400 feet, and we assumed a step out of around 6 miles. So we made some broad assumptions for the purposes of the study. We assumed that externally supplied CO2 would be tied in downstream of the subsea process station, which meant that we didn't incorporate boosting for any externally supplied CO2. We also assumed that the CO2 produced from the reservoir should be continuously separated and re-injected, so we didn't incorporate any buffer storage. We also assumed that there was enough weight on the topside, enough space and weight on the topside facility to host the power and controls equipment required. And we assumed that there was sufficient power available. In terms of battery limits, because our scope was focused on subsea processing instead of the entire CO2 EOR system, we defined our battery limits as the inlet and the outlets to the subsea station itself. And so this meant that the infrastructure for the external CO2 supply, the Christmas trees, the wellheads, the topside process and the reservoir were all outside the scope of our study. But we did simulate some of these components generically to determine the mass balance for the subsea station. So for SECARB, we considered 2 high-level concepts. So the first only includes gas-liquid separation. So the entire gas phase, including the hydrocarbon gas, is pressurized and re-injected into the reservoir, while the entire liquid phase is produced to the host facility. And then the second concept we considered includes this additional membrane separation stage. And this is used to separate the gas phase into a CO2-rich permeate stream and a hydrocarbon-rich retentate stream. So this allows us to recover the hydrocarbon gas. And generally this concept would be selected when there's enough hydrocarbon gas in the well stream to justify the extra complexity of this solution. And for the Horn Mountain production profile that we used, the hydrocarbon gas content was relatively low, but we decided to go with the more complex system to demonstrate all of the available technology and how it could be applied. Okay, so moving on to what equipment we included in each of these stages. So for bulk separation, we just included a 2-phase gravity separator. To separate the CO2 gas and the hydrocarbon gas, we included 2 stages of membrane separation, as well as a pre-treatment phase to improve separation performance. And then to get the CO2 to reinjection conditions, we boosted it in 2 phases. So first was compression to get the CO2 to dense phase. And then once the CO2 is at dense phase, then we could pump it using a CO2 tolerant pump. And cooling is also included here to increase the fluid density, which reduces the pressure to which the fluid must be boosted. We also included a multi-phase pump to boost the production stream to the topside facility. And in terms of topside equipment, we have the transformers and VSDs that are used to control the compressor and the pumps, along with some topside controls cabinets. So we simulated this system performance using HYSYS. So I've got the base case here and a sensitivity case. So the base case included the full membrane separation system. And for this, we simulated a CO2 removal by mass of 81% and 89%, with a corresponding hydrocarbon recovery of 97% and 96%. We also performed some sensitivities, which was for the simplified concept where the entire gas phase is re-injected. And we performed these simulations using 2 different inlet separator pressures. So here the CO2 removal is higher in the mid 90%, but the trade-off is that the hydrocarbon recovery is less because most of the light hydrocarbon is re-injected. And the reason that the CO2 removal is lower in the base case is because there's also some CO2 contained in the retentate streams from the membranes, which increases the total CO2 produced to the topside facility. So design of these systems is a balance between maximizing hydrocarbon recovery and maximizing CO2 recirculation. And the best solution really depends on the field. And I just wanted to talk a bit more about the technology that enables these systems. So for the compressor, we are using the Marne Energy Solutions HOFM, which is the same compressor as installed at the Åsgard field. So this is fully qualified for subsea use, but it will require some qualification for CO2 service. We used Aker Solutions standard subsea pumps, which are also fully qualified for subsea use. And testing of the liquid booster pump with dense phase CO2 has recently been completed as part of a qualification program for another project. And importantly, all tests were considered successful. So that looks like that will progress. On the membranes, we have a patented design for a compact membrane arrangement for subsea application. And the membranes themselves are undergoing testing at subsea conditions in collaboration with the membrane suppliers. And that's as part of an ongoing joint industry project led by Aker Carbon Capture. The bulk separators are fully qualified for subsea use, and the image on the screen is the actual module that's installed at the Åsgard field. The coolers are also fully qualified for subsea use. And the way that these work is we split the process fluid through many small bore pipes, and then we use the ambient seawater temperature to cool the fluid. The subsea heaters will require qualification for subsea application, but the technology is well understood topside, and we don't see any major gaps in qualifying this for subsea application. And lastly, all the power and controls equipment proposed is fully qualified and has been applied at several projects in the North Sea. So this includes the control modules, the electric actuators, the high voltage connection system, and the motor penetrators. So going forward, in budget period 2, we will design a subsea system for straight CO2 injection without EOR. And our working assumption at the moment is dense phase CO2 supplied via a pipeline from an onshore source. And as I said earlier, for this concept phase, we created a representative case study, but the next step would be to select a specific asset with with detailed information about that topside facility so that the design can be actually tailored to that case, and that allows proper comparison of the infrastructure costs. And then from there, you can start to look at qualification and verification programs for the equipment to de-risk and to optimize the system design. And we could also look at simpler system configurations for EOR than what we designed for in this phase, depending on the field. And that's everything I had. Thank you. I'll hand back to Anne.
Okay, thank you. All right, so I'm just going to give a few minutes presentation to head start what Angus is going to do next. So we're talking about the Cognac film here, which is located in the Mississippi Canyon Block 194 in the Gulf of Mexico. So as you can see on the top right, you have the location of the block right there, which is about 105 miles southeast of New Orleans. It was discovered in 1975 and it started producing in 1979. The majority of the field, the oil part, is coming from the I, J, and the K sands. So the reservoir modeling study that we did is looking at the J sand in the northeast fault block. That's the highlighted in red area that you see on the top picture there. You have a bigger picture of that fault block on the so the bottom picture here, and it only has 2 producers. There are no injectors in that fault block, and we're assuming that the new injector will be several or only 1 new injectors. We will do it for a CO2 EOR operation. Angus, can you go to the next slide, please? Thank you. All right, so this is the production history from the fault block, which started in 1999 up to 2017. So there are only 2 producers here, and the data were available for BOEM. So you can see the oil production rate for the 2 wells, gas production rate, and water production rate. Next, please. So we used computer modeling group GEM to build a reservoir model of the fault block. So we use publicly available data to build the model. So you can see all of those data in that table on your left. So an average thickness of about 40 feet, 32% porosity, 800 meter C permeability, and oil gravity of about 35 API. There's a 3D view of the model to your right, where you can see the 2 existing producers. And then at the bottom top view, the oil zone in green and the water in blue, the aquifer zone. Next, please. The picture to your left shows the history matching for oil, gas, and water. So we run the simulation on oil. So obviously we were able to perfectly match that. So with, over those 20 years, production was about like 9.2 million barrel. We matched the gas production 4.2 BCF versus 4.1 BCF, and the water production 2.7 versus 2.8 million barrel. The picture to the right shows the oil saturation at the end of the production period. As you can see, there is a lot of oil left up dip. So that's what we're going to look at for CO2 EOR on the next slide. Next, please. Thank you. So we looked at 2 different scenarios. So the first one on your left, we assumed that 2 injectors would be drilled, so 1 up dip and 1 down dip. We had to optimize that case a little bit. So when we started, the down dip injector was actually a little bit more up dip, and the up dip injector was a little bit more down dip. After running that case, so we realized 2 things. The CO2 that was injecting from the down dip injector was being reproduced really quickly at the down dip producer. So we had to shut down that producer and move the injector a little bit more down dip. And up dip, there was an area of oil saturation that still was not being properly flooded by the CO2. So we had to move the injector all the way up dip. So we had to do like several steps before we came to what was like an optimized solution. So which is what you see at the bottom. So the top left shows you the cumulative oil that was produced, and we were able to achieve 7.5 million barrel incremental oil. So incremental would be over a case where the field will continue to produce the way it was producing without any CO2 injection. And with that, we were able to store 55 BCF of CO2. Moving on to the second injection scenario that we looked at. So we decided to use only one single injector in order to limit the capital expenses. So based on the findings from scenario 1, we right away put the injector all the way up dip to try to flood as much as we could. And with that configuration only, we were able to get a nice incremental of 6.3 million barrels of oil and stored 39 BCF of CO2. So that's all for me. That was the background for Angus. So Angus, it's all yours.
Thank you very much, Anne. That was perfectly presented. So with Oudinot, we took the scenario 2 flows of CO2 and we used it to produce a demand. So for enhanced oil recovery compared to CCS, the demand for CO2 is there. It's an established amount, whereas for CCS, we're perhaps looking to either maximize use of a store, or there may be a customer whose CO2 that has specifically been provided to you to store. So EOR is driven from the flood itself. One of the issues with CO2 enhanced oil recovery, at least from a maximizing carbon dioxide storage standpoint, is that you produce a lot of the CO2 that you inject, and that's shown in the graph on the right-hand side, which is a bit complicated, but if you take the green line, which travels from the bottom left-hand corner to the right, you see that the amount of CO2 produced from the producing wells increases throughout the field life. And that in turn means that your demand of CO2 decreases because you can make use of that CO2 again to inject. And you see that in the table to the left. So over the 10-year flood, you see that by the end, there isn't actually that much CO2 required. And that also means that the amount of CO2 sequestered, which is the gray line traveling from the top left of the graph to the bottom right, decreases with time as well. And this graph is assuming that there was a 90% recovery of CO2 from the produced oil at the site. So we take our max rate of 0.59 megatons of CO2 per year and use that to size our infrastructure. So the first thing to look for is where to get the CO2 from. And this map was kindly supplied by Advanced Resources International, which is based on the Environmental Protection Agency facilities level information on greenhouse gases tool. And you can see that there's a cluster of industrial emissions. So these are non-power emissions, but there's a cluster of industrial emissions around the New Orleans area. And that's partly due to the historic, it is down to the historic oil and gas production in the region, which then led to the expansion of these industries. And that means that there's considerable optionality, to use a jargon word, in the region. So a huge amount of choice about which source you pick, and also that there'll be lots of legacy assets in the region, such as pipelines and platforms, which you can also use in your project. So there's almost unlimited options in how you can shape your the design of your carbon dioxide enhanced oil recovery or carbon capture and storage projects, at least from the standpoint of where you get the CO2 from and how you transport it to the injection sites. So we took a screening approach based on scoring of semi-quantitative criteria, which are shown at the bottom. We took landfall proximity, so the distance onshore to the point where you then meet the sea and put your offshore pipeline in to the platform. And the reasoning for that is that the offshore pipeline segments are much more expensive than the onshore pipeline segments. We also assessed on process type. So depending on the concentration of carbon dioxide in an exhaust gas, the separation cost increases the more dilute that is. So certain industrial processes produce streams of different character, and that has an impact on which facilities you'd approach to capture their CO2. And finally, the size. So we need to meet this demand of 0.6 megatons of CO2 enhanced oil recovery. It's 0.6 megatons of CO2 per year for the CO2 flood, albeit it will decrease in time. And we ended up progressing 2 facilities. The first was the Downie, Louisiana ammonia plant, although that's slightly a cop-out because it means that you have to do very little processing of the CO2 because it's close to pure from an ammonia production plant. So we chose another source as well to analyze, which was the air products Luling steam methane reformer. And it's worth noting that for this first study, we picked a pipeline concept. There's a number of ways you can transport CO2, but pipeline is the base case, if you like, although CO2 shipping is being progressed by, you may have heard, we did hear earlier from Ingrid's presentation on the Longship project in Northern Lights. But for this initial case study, we looked at pipeline transport, and in future we'll be looking to assess shipping studies as well as a potential subsea option. So for the pipeline transport, this shows a rough route. It's mostly the direct distance with a factor applied, so hence there's no detailed routing taking place. So that's from the Downie ammonia plant location to where we assume the landfill would be. And that means that we can get as short as possible offshore pipeline segment as possible to the Cognac platform. Pascagoula is marked out as the nearest LNG port, which would be looking at for shipping studies in future. And Horn Mountain and Petronius are the other 2 case studies which we'll be looking at. For each field, we're considering both CO2 enhanced oil recovery and carbon capture and storage development. So looking at the Cognac platform itself, it's a 40-year-old fixed platform in 1,023 feet of water depth. I believe at the time it was the largest platform or the deepest water platform when it was constructed. However, despite its age, structural repairs have been conducted as recently as 2012, and there was a full redevelopment in 1991. So we don't consider that the age of the platform is going to be a major constraint necessarily. It's worth noting it's a manned platform, so CO2 hazards would need to be assessed carefully, as hinted at in the previous presentation. It can be an HSE issue, but it's CO2 isn't flammable, but it presents obvious safety concerns due to its toxicity and other properties. We consider that the size of the platform would be suitable to host recycling and compression facilities for the CO2. It originally hosted more than 62 well slots, so we think that's a sufficient size and weight to host those facilities. Although for smaller platforms, it then becomes more of an issue, in that you might have to build a secondary platform to host the additional EOR facilities. There would also be enough space to host the injector. Other key concerns are less on the technical side of things. They're more to do with the commercial aspects, such as the transfer of liabilities of the platform. So who is then responsible for decommissioning? The availability of information. There wasn't a huge amount of public information available on the platform to us for this project, so we've had to make quite a few assumptions. And the timing. So when would you start your CO2 operations is a big factor, because if you don't get your development in time, the platform might be decommissioned before you can start your injection. We're looking at the overall CO2 enhanced oil recovery or CCS chain. You take your existing industrial facility or build a new one, and you capture the CO2 from that exhaust gas. That symbol roughly shows an amine liquid separation process where you have recirculating solvent which chemically bonds to the CO2 and is then heated to release it at high purity. You then take your CO2 and you compress it. Then conditioned to remove water and potentially oxygen, and then you transport it via an onshore pipeline to your landfill, where it then enters an offshore pipeline to deliver it to the platform, where it will be conditioned to the right injection pressure and temperature if required, and then injected. And the CO2 then promotes production of oil through the pressure increase, as well as reducing the viscosity of the oil in the subsurface. And then the oil is obviously then processed and taken on shore. So we split the chain into 4 sections: the capture, the transport, and facilities and wells. The methodology behind this was so that we could easily take out modules and swap them and allow sensitivity analysis to be taking place, and like comparisons between the different case studies we look at. So for example, you might change out your pipeline transport for shipping, or your facilities for subsea facilities. I've realized I've written platform versus platform, which is not what I quite intended. So we did a costing of the development, and as you can see, the wells came out as a very low expenditure item. So you've only got a single injector, and that's compared to the high cost of the recycling facilities, as well as extensive pipeline lengths. I think it was an over 100-mile 8-inch pipeline onshore, and a 25-mile pipeline offshore. So that stacks up eventually. And the capture facilities onshore, you can see that for the ammonia case, they're very little. The reason why there is a cost there is because you need to make your tie-ins and modifications to the source plant. Whereas for the hydrogen capture case, you would need this carbon capture technology, so perhaps an amine or a solid solvent technology to capture the carbon and purify it. So the key big ticket items I've listed are not in any particular order, but the onshore capture unit, the onshore and offshore pipelines, the offshore recycling and compression units, for which we use the Sleipner facility as an analog. So they separate CO2 from natural gas at their, I think it's a Sleipner T platform. And the other big ticket item is platform modification, which was highlighted in the Aker Solutions presentation as being a major driver to push you subsea. Finally, looking at the revenue, so we considered 2 oil price cases, $40 per ton and $80 per ton. And for the 45Q tax credit, we took it at its $35 per ton value at 2026, and then took a 2% interest rate that it would rise up. And you can see on the right-hand side chart that the revenue drops off very quickly, which can be expected. So you initially have a high $200 per year peak at 2022, but then this declines relatively quickly. And for CO2 EOR, you're hit with a double whammy in that your money you receive from the tax credit also decreases because you're recycling more CO2 from the well, and you're therefore storing less. So one way of potentially getting around that is to put in a second injector, and this might be either for another CO2 flood to produce more oil, although on the left-hand side graph here, we've got it simply for sequestration purposes, and you then get a tax credit at $50 per ton starting. And again, we assume that would rise at 2% per year. And what this does is it sustains revenues throughout that 10-year life and provides you a much more consistent revenue. And also provides the additional decarbonisation benefit of 5.7 megatons over 10-year life versus 2.1. So conclusions and recommendations from our report. The first thing to say is it's technically feasible from our understanding at this stage. No showstoppers were identified, although it remains to be seen with more information on the Cognac platform about how feasible that is. What is quite clear is that we require greater economies of scale to justify the infrastructure that you put in, whether that's an additional CO2 enhanced recovery well or more combined CCS approach as well. And ideally, you'd want to, if for the enhanced oil recovery wells, you would ideally want to build these out sequentially so that you can align the diminishing CO2 rates and ensure that you have a more consistent profile of demand. And that would also mean that you'd have a more consistent revenue stream as well. Perhaps the best thing to do though is to use the onshore pipeline you deploy to feed multiple offshore developments. And I think Advanced Resources have done some work on this already. And I think you saw an image in the Aker solutions slides showing this. And what you find is that the costs of deploying a pipeline don't scale hugely for larger diameters. And you can achieve much higher economies of scale there. We did look at legacy pipelines in the region, but what we found is that the design pressure can pose problems. So for CO2, you ideally want to transport it in its liquid or dense phase. But to do that, you need to keep it above its bubble point to stop gas breakout. And that requires quite high pressures, which oil and gas pipelines might not be designed for. So they sometimes are, so you can sometimes find useful pipelines, but often they'll have a lower design pressure than what's required. And that's what we found so far. For future work, as I said, we're going to consider some ship transport cases, and ship transport really favors shorter project durations or smaller scales. So it'd be interesting to see how those economics compare to what we've looked at here. Also potentially onshore pipeline versus barge. This is not something we're going to look at, but it's perhaps particularly suited to the Mississippi region, so you wouldn't have to route a pipeline through potentially difficult terrain. And this has been looked at in various projects in the Netherlands as part of, I think, the Porthos project. And finally, you'd need to assess the legal and commercial implications for platform reuse, such as liabilities, as I mentioned. I think we're due for questions now.
Great, thank you so much. We do have a number of questions. I see that Mike Godek has his hand raised. So Mike, why don't we start with you?
Okay, thank you. Good presentation, Angus. I get 2 points I want to make. One is that as you showed that one graphic that really showed, the pipeline going from onshore to offshore to Cognac, and then it would be very easy then to take that to Horn Mountain and to Petronius as well. And it really kind of sets up a kind of an interesting logical case for a phased development as you go out to kind of overcome that severe decline in CO2 requirements, after a few years of production by sequencing those fields in a reasonable way. Yeah, exactly. And so that's kind of one way. And clearly, people like OGCI and others are really now looking at these regional hub kinds of structures. And as you said, there's no shortage of supply of CO2, and it should be relatively straightforward to that. The other point I make, and I just see that Darshan is commenting on this, he made a presentation last week at an SPE workshop that indicated that there are possibly some legacy pipelines that could be feasible to use. Whether exactly they're in this location to take care of this sequence or not remains to be seen. But it is conceivable, perhaps, that some of the newer pipelines that are, that are scaled to the higher pressure could, in fact, work at it. So I think one of the things we're going to want to look at, you and I haven't talked about this, Angus, yet, but really look at kind of what a phase development might look like as we link these three individual cases together in a sequence.
Yeah, there's some good points. It's also worth probably pointing out that for CO2 enhancer recovery versus carbon capture and storage, you have the issue where the pipelines which you might want to use for transporting CO2 to the platform are being used to transport oil and gas the other way. So often the opportunities arise more for the carbon capture and storage projects.
Yeah, but and yeah, I mean, logistics are key to this whole thing, and that working that out is going to be a major challenge. Thank you, Angus.
Great. So we did have a few other questions in the Q&A window here. One attendee asks, how do you manage the corrosion in the injectors and producer wells caused by the CO2? I suppose that's probably for all panelists in this session.
I can answer that potentially. So for corrosion, you can either dehydrate the carbon dioxide, or you can specify corrosion resistant alloys, and the way you go will depend on the individual economics, but obviously when you produce the oil and the CO2, it's going to be the CO2 that you separate from that will be water saturated, so that can increase the cost if you don't then dehydrate it. And it's the same reason why you dehydrate it before you transport by pipelines, is and that then allows you to construct using carbon steel.
Okay, great. And we have time for one more question here. Sue Havorka has asked, you specifically, Angus, have you considered modern regulatory and environmental limits on construction of pipelines in the wetlands of Mississippi's Delta? Well, the Mississippi Delta, excuse me.
We haven't, no, and I think that's definitely been at the back of my mind, is that how easy would it be to produce a pipeline in that area, and that's why maybe in more detailed level of study you'd look at alternative options such as barges or shipping from an alternative site such as Pascagoula. But I think what the purpose of the case studies was mainly to provide these representative costs.
That sounds great. It looks like Mike wants to jump in here.
Yeah, I think that's a great question. And, eventually as part of the second budget period for this project, linking kind of the infrastructure questions with the regulatory considerations is something in this project that remains to be done. So that is an issue that we plan to explore in budget period 2.
Great. Well, thank you again to our panelists. This will be our final session of the day. We'll be discussing seismic hazard assessment and earthquake risk analysis. Our first presentation will be given by Camelia Knapp, department head and professor at the Boone Pickens School of Geology at Oklahoma State University, and James Knapp, Boone Pickens Distinguished Chair. After that, we'll hear from Charlie Schlosser, the research associate at Virginia Center for Coal and Energy Research at Virginia Tech. Charlie will be discussing predicting the dynamics of injection-induced fault slip. Take it away.
Thank you, Ben. Can you see my screen?
I can.
Okay, thank you. Well, good afternoon, good evening. It's a pleasure being here as always, and I will switch gears. Our work on the SECARB Offshore team is under risk assessment. That's task 4. And today I will talk about gas hydrates. Why gas hydrates? Because they could be natural hazards with respect to CCS infrastructure in the Gulf of Mexico. So other than myself and my lovely husband, Jim, we also have two students who've been working on this project. Gökçe Aztekin, who just finished her master's a few months ago, and Saiful Alam, who is doing his PhD. In the acknowledgements, other than the SECARB Offshore team and SSCB and DOE, I particularly want to acknowledge the Gulf of Mexico Gas Hydrate Research Consortium, under which this project started many years ago. However, it just happened that toward the end of the consortium, we were able to secure quite a number of geophysical data sets that we are working with under this project. So this shows the location of MC118, that is the focus of our work. MC118 is on the continental slope of the Gulf of Mexico, down deep and southeast of the Mississippi River Delta. And the Woolsey Mount, as we subsequently named it, was named like this in memory of Bob Woolsey from the University of Mississippi, who was the founding chair of the Gulf of Mexico Gas Hydrate Research Consortium and passed away during the time the consortium was active, unfortunately in a car accident. The Woolsey Mount is located in 900 meters water depth on the northern continental slope of the Gulf of Mexico. And as you can see in this picture, that's MC118, the slope here is highly discontinuous, intersected by slumping, folding, and faulting, mainly driven by salt tectonics and sediment load delivered by the Mississippi River. And here I show a picture that was taken from a ship at MC118 that was on a research mission while the Deepwater Horizon accident occurred at Mississippi Canyon 252, only 10 miles away. And I strongly believe that gas hydrates had a lot to do with that accident, other than many other things that went wrong. The Woolsey Mount is what we call a cold seep hydrate system, which is a dynamic setting where hydrates form and dissociate on variable timescales, triggering substantial methane fluxes to the oceans. And understanding how these cold seeps operate through time and space, we believe is important to evaluate their global impact on ocean biogeochemistry and climate. However, to thoroughly understand what governs marine cold seeps, an integrated approach should include investigation of several things, including the deep oil reservoir where thermogenic gases originate, the plumbing system where the hydrocarbon fluids transit, the shallow subsurface where hydrates form and accumulate, and the seafloor ocean interface where hydrates are exposed and gas is expulsed. Cold seeps develop unique topography over time, and reactions between methane and seawater usually creates carbonate rock formations and reefs. And also these reactions may also be dependent on bacterial activity. They're really highly complex and dynamic. And here is our Woolsey Mount. And you can see here they are pervasive throughout the Gulf of Mexico. I think the last count that I've heard was around 600 cold seeps in the Gulf of Mexico. What's also important is that it's estimated that about 47% of crude oil currently enters the marine environment from these natural seeps, whereas 53% results from leaks and spills and transportation, extraction, utilization of petroleum and all of that. At Woolsey Mount, hydrates form from vertical migration of hydrocarbon-rich fluids that reach the hydrate stability zone. defined by overlying pressure and in situ temperatures, and that precipitates as gas hydrate. Periodically, this migration reaches the seafloor and creates a seafloor habitat full of outcropping hydrates, chemosynthetic communities, carbonate mounds, and bubble plumes. The Gulf of Mexico Gas Hydrate Consortium chose this location because it is a viable gas hydrate monitoring site due to gas venting at the seafloor, outcropping hydrate mounds, presence of chemosynthetic communities, lack of existing ownership, and it still is designated as a research area, and relatively shallow water depth, which is less than 1 kilometer. Lithologic and biogeochemical studies have been done on sediment samples from gravity and box cores, and pore fluid analysis carried out on this course revealed that microbial sulfate reduction, anaerobic methane oxidation, and methanogenesis are important processes in the upper sediments. 3D industry seismic data revealed the presence of a salt body in the shallow subsurface in our study site, and this generated an extended network of faults, as shown in here in a 3D view, and here is the map view. Some of these faults extending from the salt body to or close to the seafloor. We called these faults master faults, originating from the salt body underneath. Higher resolution seismic data that I don't show here today, that's SSDR or shallow source deep receiver, showed acoustic wipeout zones along the master faults with expulsion features at the seafloor, pock marks, and craters that were located immediately above these interpreted faults. We also noticed high amplitude negative polarity reflectors relative to the seafloor at an approximately constant depth of about 0.2 seconds below 2A travel time below seafloor. And that is about 150 to 200 meters below the seafloor. Since pock marks and craters provide pathways for hydrocarbons to escape from depth into the water column, related subsurface seismic anomalies may indicate free gas at the base of the gas hydrate stability. Based on shallow cores and the seismic interpretation, it seems that vent activity at Wilsey Mound in the past moved from the southeast crater that is bound by this yellow fault to the southwest complex that is bound by this pink fault, and potentially more recently to the northwest crater along this blue fault. And you'll hear me talking about with these faults next. And also the microbial activity, as shown in here, shows temporal evolution from the southeast to the southwest to the northwest. Due to the geologic, structural, and thermal complexity of the Gulf of Mexico, the gas hydrates here do not exhibit the classic regional BSRs or bottom simulating reflectors on seismic sections. Those are usually clear markers on seismic lines. They mimic the seafloor, and they are reverse polarity, but bright, really high amplitude reverse polarity reflections relative to the seafloor. So hydrates in our study zone seems to form around salt-related faults that provide likely migration pathways for the thermogenic hydrocarbons. And clearly we need other methods to identify them in order to provide estimates of their presence and their volumetric extent. And here is actually, this was a 6-inch diameter core taken right here. This was the jumbo piston core cruise in 2011. And in this whole area, there were several sampling sites, but this was the only site that actually brought hydrates to the surface. They look like nodules, a little less than 1 inch thick in thickness. And again, this is JPC1. That's the location where that sample, that core comes from. And these were actually fairly shallow, about 25 feet below the seafloor. Given specific geothermal and geochemical conditions of our study area, we calculated theoretical phase equilibrium diagrams. They show the temperature and pressure at which hydrates form from a certain gas composition, as shown in here, very thermogenic with 70% only methane. And these concentrations were used from a paper by Sasson et al. 2006. Our calculations were defaulted to 4.885 degrees C seafloor temperature and 3.5% pore water salinity. So the area on this graph defined by the gas hydrate stability curve, this is depth in meters, pressure in atmospheres, and temperature in degrees C. So this area between the stability curve and the geothermal gradient defines the gas hydrate stability field. In other words, the temperature and pressure conditions at which hydrates potentially form given all of these different parameters, and showing here a maximum thickness of over 1 kilometer. All right, so moving forward, based on what I was just describing, these were a set of hypotheses that we built for the Woolsey Mound, that gas hydrates are genetically related to the salt system in the subsurface through active normal faults that are conduits for thermogenic gas. Formation and dissociation of hydrates vary temporally in the vicinity of these active faults. The gas hydrates at Woolsey Mound are controlled by a highly heterogeneous stability field that leads to the paucity or the scarcity of bottom simulating reflectors at our study site. And we believed that in the absence of having these indicators on seismic lines, amplitude versus offset analysis would be a good indicator of hydrates in the absence of identified BSRs. So here on the right side, I show a cartoon with the inferred mechanisms governing gas hydrate formation, accumulation, and stabilization at that location where we found hydrates at JPC1. So at time 0, as shown on the left, gas hydrates are stable along the blue fault and clogged thermogenic gas migrating upwards along the fault at the base of the hydrate stability zone. At T1, moving toward the right, I don't know if you see probably don't see my cursor. Free gas accumulates at the base of the hydrate stability zone, building up pressure as it cannot migrate laterally due to the absence of high permeability sediments. In C at T2, when the upwards pressure exerted by the free gas exceeds both the mechanical strength of the overlying clatrate and the hydrostatic pressure, thermogenic gas breaks through the overlying fracture filling hydrates, promoting dissociation and seafloor venting. And then the last scenario is where gas hydrates begin forming again once the dynamic equilibrium of T0. So that was the early stage being reestablished. So, and then the cycle starts again. So that's kind of the scenario that we are going after in our analysis. Yeah, we can move next, Ben. These are our available seismic data. So we do have 4 seismic volumes, pre-stack and post-stack, including stacking velocities from the Woolsey Mount. They are all shot across the Woolsey Mount, which I should have mentioned. It's a 3 by 3 mile. It's the regular exploration block size in the Gulf of Mexico. So the TGS NOPAC data are 3 seconds only, 2-way travel time, but we got 10 seconds from the 2003, 2010, and 2014 data. So we are working on this data for both AVO analysis and 4D time-lapse analysis. Yeah, we can move next, thank you. Okay, so here are just some preliminary 4D seismic data. Cypher is working on this, but these images show a time slice at about 1.3 seconds. And that shows different volumes created from the 4 3D data sets over the Woolsey Mount. The changes in amplitudes represented by the blue and reds appear to document changes with time in the physical properties of the subsurface, which we interpret as evidence for changes in fluid volume and composition. So I guess at this point, that's all we can say about this before further analysis. Next, Ben. Yeah, this doesn't show the whole thing. Okay, so here we show the amplitude versus offset premise that we started with. So in contrast with the classic interpretation that the top of gas sands should show an increase of amplitude at far offsets, recent studies, actually starting with Castagna 98, although he was not talking about gas hydrates, he was talking about with carbonates, for instance, that have higher P wave and shear wave velocities than the underlying sediments if they were shallow. So anyway, so this study suggests that gas sands may exhibit a variety of AVO behaviors, and prior knowledge of the expected gas sand AVO response is required. So I think that's the next slide. But anyway, in the calculation of the reflection coefficient, there is a 0 offset component, which is basically the P wave reflection coefficient, and a far offset component that takes into account also the shear wave reflection coefficient. So at 0 offset, the amplitude depends only on the compressional wave velocity and density, but that contribution at the further offsets is very important to identify these different classes. So we identify hydrates as class 4, low impedance, P wave reflection coefficient decreases with increases angle of incidence, and they typically occur when porous sand is overlain by high velocity unit, including gas hydrates. Okay, so we can move next. Yeah, here shows how real data kind of clusters in the AVO gradient and intercept cross plots. What we are kind of expecting is what shows here in the second quadrant, going from top right to left, and that's the hydrate. And I will show some of our data, how they plot in this AVO intercept charts. So if we go next. Okay, so that's one of the first one. So there's the AVO gradient and cross plot analysis at the Northwest complex, and that's along the blue fault that I showed earlier. This was the first analysis that we did on AVO, where gas hydrates were, and this is where gas hydrates were recovered, as I said earlier, during the JPC cruise. And this figure shows side-by-side peak cross lines for both data sets, 2000 and 2003. I only show these two different times. And we compare the seismic features to delineate the bright spots on the interest. So so as shown here, both cross lines show similar features, and the high amplitude bright reflectors around the red and blue faults were the ones that we did the AVO analysis at. So here the scale bar is fuzzy, but the total length is 2 kilometers. So what's shown here circled in white is where our bright spot was. The further inference would be that that could be a BSR. However, again, they don't really look like classic BSRs. So this is about 500 meters long. So if we go next, Ben. So here we show the result of the AVO analysis, and all cross plots shown here that peak events are located within quadrant 2. Is that what we would expect for class 4 or hydrates? So also the gradient curves indicated the absolute value of the amplitudes are decreasing with increasing offsets across the interface that was studied at what we believe is the base of the hydrate stability field. And we interpret this signature as presence of free gas below a higher velocity layer, which we assume it's hydrate. Going next, we are showing a similar analysis now at the southeast complex. This was along the yellow fault. And here the bright spots are slightly shorter. The scale bar here is 1 kilometer in length. If we go next. Yeah, so we show here the AVO responses for the peak bright spot from 2000 and respectively 2003, and also indicate class 4 AVO response. So again, consistent with what we believe to be free gas underneath a tighter material like gas hydrates above. Next. That's the last one that I'm showing, and this is above the, this corresponds with the southwest complex, and this is across the pink fault in particular. So this area was close to a core location that did not find hydrates. However, at the time, they saw gas expansions and blisters at this particular core location. And here we show, again, 2000 and 2003 seismic lines, and the bright spot here is located between the red and the pink faults around the southwestern complex. Next. So these are the cross plots for the southwestern complex, and again showing class 4 anomalies. Even though here the AVO responses seem to be weaker in terms of the reflection coefficients and how they vary with the angle of incidence, it all seems to be consistent. That this may be free gas that is overlaid by a high P wave velocity, high S wave velocity layer. And in those very shallow sediments, there aren't too many lithologies you can think about. In general, these are very unconsolidated sediments. Actually, here we don't necessarily have gas sands or sands. We have lots of muds, so definitely finer material. But other than carbonates and gas hydrates, you really are hard pressed to think what can create these high P wave and S wave velocity anomalies in the very shallow sediments. So we are talking here about 150 to 200 meters below seafloor. Okay, next slide. Okay, so yeah, I did have this changed, but I will just go by these conclusions that the high amplitude bright reflectors that we studied appear to mark the base of the hydrate stability zone. And the AVO seems to be a good alternative for identifying hydrates in the shallow subsurface. And the AVO results are consistent with some of the previous 4D time-lapse studies that now we are continuing with the additional data sets that we have. And the mound activity shows, even within the 3-year change that I show in this talk, that hydrate formation and dissociation really can occur on these very short time scales. You know, the gas hydrates at Woolsey Mound seem to be controlled by this highly heterogeneous stability field that is controlled by changes in salinity and temperatures, as well as that, well, and driven by salt tectonics. Okay, I will leave it here. Thank you, and again, apologies for the glitch.
Oh, thank you so much. With that, we'll move on to our final speaker for the day. Again, that's Charlie Schlosser, and he will be discussing predicting the dynamics of injection-induced fault slip. Charlie?
Thank you so much for sticking it out on the last presentation of the day. So my presentation and my work has been focused on predicting the dynamics of injection-induced fault slip. I've been, as part of my contribution to the SECARB Offshore project, I've been developing software to look at this problem, and it's also the subject of my PhD research. So I've always been interested in this because injection-induced seismicity is a concern to all carbon storage project stakeholders. Even if you're personally not concerned with it, I think you are concerned that the general public is concerned with it. Felt seismicity is a real hazard, and all seismicity carries a negative connotation with carbon storage projects. Existing methodology can predict the conditions under which fault slip occurs with reasonable certainty. Often just with hand calculations, there are a number of researchers who put together very sophisticated models coupling fluid flow and poroelasticity, reservoir simulation, and that's even better. But less tools are available to predict the outcomes of a hypothetical fault slip scenario. And I'm interested in, okay, so slip does occur. What is the magnitude of the event? Is the event felt? And could this information be used to inform carbon storage project design and address other issues and other stakeholder concerns? So as a brief overview of injection-induced seismicity, an inactive fault is a mechanical equilibrium. There's always some lithostatic stress applied to the system. There's always a little bit of pore pressure, but in general, the frictional capacity of the fault exceeds the shear loading, and the whole system behaves like a continuum in equilibrium. But there are situations where if you increase that pore pressure, perhaps from the far field or even closer to the well, where now that you've upset that equilibrium and the shear loading has exceeded that frictional capacity, which results in irreversible relative motion between the bodies. This could be a felt event, it could be very large. It all depends on the conditions. So it turns out most fault friction models are based on a very simple law called Edmonton's law. And a lot of people call this the Moore-Coulomb failure criterion because the forms are very similar and they essentially work with the same principles. The law governs the maximum ratio of shear to normal stress. Pore pressure acts in opposition to lithostatic pressure, and this is also called Tergazzi's principle. The friction coefficient can be constant or state-based. There's a lot of very fancy rate-dependent friction laws that are popular in earthquake modeling, which I also want to investigate at some point, but right now I'm just using a constant coefficient. Relative displacement constitutes mechanical work performed on the fault, which is the seismic energy that we potentially can feel. So I set about to define a very simple system, just an idealized fault system, two linearly elastic rock bodies in contact at a frictional interface. These bodies can exhibit rigid body motion and elastic deformation. The external loads, there's triaxial stress at the boundaries, horizontal stress, vertical lithostatic stress, and also body forces, which are gravity and internal pore pressure. At the fault interface, I have some constraints, which are that the rock bodies cannot penetrate through each other. They can transmit energy across the interface, but they can't actually intersect, and also Coulomb friction. So just a brief overview of linear elasticity. Stress is defined at each point in space by actually a 3x3 matrix. If you assume there's no internal torque, which is almost always a valid assumption in this kind of work, you actually have 6 unique values. And these values can be reduced to principal stresses, which are the eigenvalues of the matrix. Strain is the gradient of displacement, which is also symmetric 3x3 matrix. And the traction vectors, which are what we're used to talking about, which is the normal stress acting upon an interface and also the shear stress. This is a resolution of that stress tensor onto a plane of interest. So the finite element method, many of us, including myself, are more familiar with finite differences, which are used in the reservoir simulation community. And there's a special case of the finite element method. The concepts are similar, though finite element method is better suited for regular and dynamic discretizations. Essentially, this method is applied to the linear elasticity equation, which is the same, it was on the slide before, just in a more compact format. And the approximated displacement is defined at each node of the mesh. And this is just standard finite element methodology. There's a lot of very esoteric books out there on the subject matter, but it's not as complicated as it appears on here. Basically, at each element, you have a set of displacements and the gradient of those displacements, which is the strain, and those are related to stresses through a linear transformation, which is defined by Young's modulus, Poisson's ratio, and all those usual things we see in rock mechanics. Essentially, the problem is reformulated into a quadratic form, whereby when you minimize that energy, you get the true solution. And this is related to the principle of least action. It turns out in nature that the universe tends to take the path of least action, and that's exactly what we're solving for in the finite element method. So to do this, I wanted to solve the dynamic linear elasticity equation with the finite element method. I'm using linear tetrahedral elements, and some people think that these are a little too not flexible, but as you see in the picture here, if you can model the human heart with linear tetrahedral elements, I'm sure you can model a rectangle, as my model is basically. There's 4 nodes per element, 3 displacement degrees of freedom per element. Each of those has 3 dimensions. And all of these nodes are shared together so that the whole system is coupled. So there's a lot of existing software to deal with this, but it's very difficult to find something that kind of checks all the boxes that I need for this problem. Something that does the finite element, something that handles the Coulomb friction at the interface, and also something that addresses internal pore pressure. And there may be a package out there that does all these things, but it wasn't apparent to me in my search. And there's also some advantages to making your own software. You can extend it and adapt it. You can couple it to other software like GEM for reservoir simulation. So it was also just a personal interest to me. So the first challenge I came across was if I have these 2 rock bodies which are basically independent of each other, how do I make sure that stress is transmitted between the 2 bodies so that I can simulate that earthquake while still allowing rigid body motion between them? And it turns out that this was not too difficult. I just have to, there's a standard method for doing this, and I implemented it in my solution. And just as a demonstration that it works, I put 2 very irregular or dissimilar meshes next to each other. And the cell stress is definitely continuous across the fault boundary. But the trigonometry involved in this was actually the real challenge. I learned very quickly that there is a very smart community of professional computational geometers out there who all day long they deal with intersecting triangles, determining if 2 lines intersect, stuff like this. So the best thing to do is, if you're working on this algorithms, use somebody else's geometric library. And while I wasn't too worried about optimization, I was just worried about getting the right answer. It's way too slow to do this unless you employ a few tricks. One triangle intersection is fast, but doing a million every time step, it's way too slow. So there's a trick called a bounding volume hierarchy, where you draw a bounding volume over each object, and you can perform a very cheap check to see if there's contact between the elements. And if there is, then you can call the very expensive check. And if not, you move on. So I can perform the intersection of the image you see up here in less than a millisecond on my laptop. And before this optimization, it was taking about 10 minutes per time step. And then the second challenge was incorporating internal pore pressure into the finite element framework. It turns out that this is actually really easy. It's just a obscure problem for a lot of the commercial software out there, whereas it's a very common problem for people in, geological field of interest. So I just treated it as a body force, which is kind of like gravity. Since pores are pervasive throughout a rock, pore pressure and the effects thereof are also pervasive throughout the body. It turns out that's very easy to incorporate into the framework, and very little modification is necessary. So if I got a reservoir simulation output of pore pressure, I can map it onto my finite element mesh and include those effects in the stress calculations. Now, the hardest thing is enforcing Coulomb friction on the interface. It's a very innocuous appearing equation, but it's very difficult to enforce. But it turns out if you can re-express that same failure criterion into the form you see below, which is the tau squared minus mu squared minus sigma n squared, it actually becomes very feasible to incorporate this constraint to the optimization. So the advantages of this constraint are it's completely differentiable. It's a very clean mathematically. The matrix is indefinite, which means it could be very difficult to solve, but if you add the constraint that normal stress is always positive, and which it always is in the cases of interest, then this problem is convex. And I wasn't even sure what convexity was, but I learned that it's very important. What it means is the problem is solvable. So it means that if you do find a solution, it is the unique solution. And that's very important when you're working with simulating the elastic response of the body, because you want to make sure that you're minimizing the energy, and then that earthquake, that your model that you're trying to simulate is actually, you're getting the correct answer at each step. So putting it all together, I have the usual elastic potential energy, which is the K term. I have the dampening effects, which is the C term, and I have the inertial effects, which is the mass. And also I have the contact forces between the two bodies, and I have the boundary conditions, which is the triaxial loading, the gravity, and internal pore pressure. And I have to subject it to these constraints. And the minimum energy solution has this following form, which is called the saddle point system. There's a million ways of solving this. When the constraints are not violated and no slip has occurred, you can continue on, but when the constraints are violated, you have to enforce the constraints. And currently I'm using interior point methods to do this. And this is sort of the subject of my future work, is to fine tune that. I have it working to some degree, but I need to improve the numerical precision. So far I've basically implemented the software package using all free and open source software. The big one is Eigen, which is fantastic. It's used by Google for their machine learning stuff. It's free for commercial users, academic users, anybody really. Sweet Sparse is another one. CGAL for the geometry, and PairView. It's not open source, but it's freely available. Good data visualization tool. I've incorporated some of the less common concepts into a finite element framework, which is the linked subdomains of the fault system, the effective stress, Tergazzi's principle, and the frictional interface. And more importantly, I've demonstrated this is a very solvable problem requiring very modest resources. I didn't spend $1 on software. And I think this is important if you want people from across disciplines to use it, or often commercial firms are precluded from software because they can't afford it, which is kind of ironic, but at least in my experience, the private sector, I couldn't get any of the software I wanted. So I really like free stuff. And future work, I need to improve that enforcement of the Coulomb friction criterion. I really think it's caused by numerical precision limitations in real world problems, especially geologic problems. You have variables that have many orders of magnitude separating them. You know, you have stress measured in megapascals, displacement measured in millimeters over a domain of kilometers. So I think if you more carefully handle how those variables are treated, you can solve a lot of the issues from the get-go. And currently I've sort of naively just plugged in all my unscaled magnitudes in there. For instance, I square Young's modulus, and then I take the natural logarithm of it, and that I lose a lot of precision every step. And I also need to develop a case study to validate the model. Currently, I'm looking at the far field pressurization work that has been studied at Fairview, Oklahoma, those injection-induced earthquakes. And I also need to look at an idealized sort of or representative offshore case to see if this tool is useful to the rest of the work being performed as part of the SECARB Offshore project. Thank you. And if there's any questions, I'm happy to answer them.
Excellent talk, Charlie. Thank you. Okay, so at this time, we'll take questions for Camelia or Charlie. I did see one question from Sue in the chat that has not been answered. Here we go. So she asks, Charlie, do you have good sources on geomechanical properties of Gulf of Mexico, very young and poorly indurated faults?
No, I would love to have some.
So we might, so this is Sue, we might offer you collaboration with Josh White at LBNL, who's working on GoMCarb on some of the same issues. So if you haven't met Josh, please reach out to him. He'll be presenting tomorrow, or Josh White, Lawrence Livermore National Lab, sorry. It's late in the afternoon to make this slip. Apologies to my lab friends. Josh White at Livermore has been working on GoMCarb related problems, different modeling strategies. Anyway, if you guys could be of any help to each other, it would be great.
Thank you.
Okay, are there any other questions? Yes, Jack, go right ahead.
Yeah, just a question I have. You know, induced fault slip is one of the things that really interested in, especially, you know, dilation tendency and slip tendency. And when you get into undercompacted systems and systems with a lot of hydrocarbon charge, you know, a question I have is how much pressure increase from injection can obviously contribute to dilation and slip, but also deflation of units by depressurizing. And if you run a production well a little too hard adjacent to a fault, that could probably cause slip too by distressing the system and causing things to slip because of compaction. So I wonder if Charlie, do you have any ideas on that?
Fortunately, I've tried to make as few assumptions as possible so that you know, I could possibly, you know, implement my solution to situations that I haven't even considered, because all I'm really doing is enforcing Moore's friction law and letting, you know, Newton's laws of motion sort of take care of the rest. So I think this software could be applied to that, as long as I have good information on, you know, is the Coulomb friction coefficient rate dependent, or is it constant? And also are the elastic parameters, you know, Young's modulus and Poisson's ratio, are those constant, or do they change based on a state? I'm not saying it'll be easy to incorporate those, but I think it's doable. And I don't know the answer ahead of time, so that's why I like developing tools like this, just to let it run to see if there's you can glean the information from it.
Yeah, it'd be interesting to see how things come out. You know, I guess one thing we have a lot of is pressure data, and that can really help because, you know, that kind of tells us where the failure point is and where reservoirs naturally sit relative to that. So it's kind of, you know, looking at changes of stress related to changes of pressure may end up being a really important thing for, you know, ensuring security when we're working in faulted areas.
I agree.
Okay, any more questions? Okay, hearing none. Thank you to our panelists for a day of informative presentations, and thank you to those in attendance for your participation. We ask that you please join us again tomorrow for the GoMCarb update and theme presentations. All presentations will be made available to the public once the meeting has concluded. For future Southern States Energy Board events, please visit our website or follow us on Twitter or LinkedIn. For general questions related to the SECARB Offshore program, I ask that you please reach out to me directly. My email is provided there. For technical issues related to Zoom connectivity in this meeting, please reach out to Turney Foshi. Thank you again, and with that, this concludes the first day of the SECARB GoMCarb Joint Partnership meeting.